Okay, so welcome back everyone to our last day of the conference. And let me briefly remind you that in order to ask questions, please use the raise hand feature or write your question in the chat, and then I'll give you the word to ask your questions either during the talk when Martijn is happy with that, or afterwards. Okay, also some small announcements. So the conference picture is now online in Slack. It has everybody in it who was there on Tuesday and had their cameras on. But if you still want to be added, that's possible. Just send me a picture screen shot and I'll add you. Okay, so without further ado, it's a pleasure to have Martijn Hidding here telling us about solving elliptic and more general Feynman integrals through the expansion method. Please.
Okay, thank you very much. Thanks to all the organizers for allowing me to give a talk here. The topic of my talk is series expansion methods for Feynman integrals and for Feynman integrals that are beyond elliptic. So as an outline of the talk, I will start by discussing the method of differential equations, which is kind of underlying most of what I will be talking about. And then I will discuss how by solving differential equations along one-dimensional contours, you can, and finding series solutions along these one-dimensional contours, you can obtain high precision results for many Feynman integrals. Now, some time ago, I released a package called DiffExp that automates some of these methods, and part of my talk will also be about the use of this Mathematica package. Now, I'll discuss a few applications. So I will in particular talk about some banana graphs, tree loop, and even a for loop example. And then I will also discuss some Higgs plus jet integrals that we computed in a large collaboration in the past, and which provides some context for all of this. So let us first have a look at the different ways of computing things. So one way of doing it is to use analytic methods. And I think analytic methods are very popular among the people in this conference. It basically involves expressing Feynman integrals in terms of classes of iterated integrals, such as MPLs and EMPLs. And the advantage of this is that when you solve things in terms of such functions, then the algebraic properties are usually manifest. And you can use nice things like a Hopf algebra and a symbol map to simplify your expressions. And also, in many cases, you get good numerical performance. So especially in the case where you have polylogarithmic solutions, the performance can really be very good, and you can sometimes obtain hundreds of digits. But a drawback of analytic methods is that the analytic continuation can be quite complicated, and in general, it's not known how to obtain analytic solutions. It's mainly the last one, which is the main problem, that there's many integrals that we just don't know how to compute them fully analytically yet in terms of some class of iterated integrals. So then on the other side, you have numerical methods. This can be things like sector decomposition combined with numerical integrators, where you're just numerically integrating your integrals in a very generic way, which is kind of blind to the integral that you are computing, but it's very general purpose. Now, the benefit of this approach is that it's quite simple to do, but the drawbacks are that you might not see, say, symmetries that you would see in the symbol. You don't see some cancellations of letters. And also the performance can greatly lag behind analytic methods. So an intermediate strategy is to use the method of differential equations. So you derive differential equations for Feynman integrals, but now instead of going fully analytic, you say, I'm satisfied with the differential equations and I'm going to solve them numerically. And in particular, one way to do this is by iteratively doing series expansions of the differential equations and finding series solutions. So the general strategy that we'll be following comes from a paper from Francesco, where he applied such methods for the computation of planar mass integrals for Higgs plus jet. And basically at the same time, I was part of a collaboration, including many others, where we were computing non-planar Higgs plus jet integrals using similar methods. So I'll talk a bit more about this later. And the main steps of this approach are you write down a sequence of line segments to any kinematic point which you're interested in, and then you segment it. And then along each segment, you expand the differential equations and you find series solutions. And this way you can overcome problems with the radius of convergence of the expansions of the individual segments and actually transport numerical results to any point in phase space and at a very efficient way. Now, this idea of solving differential equations using series expansions is of course not new. So there have been many things in the literature, many papers in the literature dealing with these kinds of things, but usually it was in a more restricted settings. So for example, there were quite a few papers dealing with single scale problems. And there were also papers dealing with multi-scale problems, but then usually the way that it worked is that you expand one scale and you keep the analytic dependence on the other scales. Now, so one paper that I want to, or some papers that I could point out are, for example, the papers from Roman Lee, Vladimir and Alexander Smirnov, which dealt with evaluating elliptic Feynman integrals by expanding near special points such as thresholds. And this is actually fairly close in spirit as well to some of the things I'll be discussing, especially since the banana graphs that I'll be computing are also one-dimensional. So to move on. Now, before all the codes that were dealing with series expansions, they so far they've been kind of private and problem tailored. And so this package DiffExp, which I recently released, the idea is that it allows you to take in any system of differential equations that comes from some dimensionally regulated Feynman integrals, and in principle that you can solve the differential equations in terms of series. So some of the uses of such a package would be to compute the Feynman integrals numerically at high precision, or if you already have some results somewhere, maybe you want to do the analytic continuation across a threshold. For this, the package could help. And similarly, sometimes you have boundary conditions in a special point, and usually, so special points like thresholds or things where masses vanish, the results can be very simple there, and you can use the package to transport boundary conditions from one point to another. So, and to continue, so in the method of differential equations, the way it works is that we start from some family of scalar Feynman integrals, and well, by IBP reduction, we know that there's a finite basis of integrals in terms of which we can compute the whole family. Now, if you start taking derivatives of any Feynman integral in the basis, then you just introduce some dots and some numerators. And so by this IBP reduction, you can go back to your original system of mass integrals, and then you obtain a closed system of differential equations of the following form for some choice of mass integrals. Right, now a very powerful way of solving the differential equations came from the introduction of the canonical basis by Johannes Henn, who observed that if you do a appropriate change of basis, then sometimes you're able to factor out the epsilon dependence, and then you get this nice form here, where you have, say, a total differential, and this dA tilde matrix doesn't depend on epsilon anymore at all. And then you can iteratively solve the differential equations order by order in epsilon. Furthermore, if the integrals are polylogarithmic, then you can even write things in as a sum of d logs. And of course, we now recently know that the reverse is not true from the paper by Claude Doer and Francis Brown, where they showed that certain d log integrals are not necessarily polylogarithmic. Now, if you have such a canonical basis, then of course, solving everything is very simple because the general solution is given in terms of chance iterated integrals. So, and really, I highlighted the formula here on the slide. So to reach the next order in epsilon, you just multiply by the differential equation matrix, and then you integrate. And of course, if you do that iteratively, then you get the longer formula that's at the top here. Now, so when your total differential is a sum of d logs, and also when you have only rational functions or roots that can be rationalized, then this path ordered exponential here, it can be expressed in terms of multiple polylogarithms. And so that's really good because now you have a fully analytic solution. And also we know that with GNAC, you can get very high precision numbers out of MPLs. But of course, such a canonical form is not always available. And when you have these non-rationalizable square roots, it might not be possible to solve your basis in terms of MPLs. So then this series solution approach might help out. So if you consider some contour gamma, which is some line in phase space, and we parameterize it with a parameter x going from 0 to 1, then of course what you could do is you could expand at this origin of this contour, and you would just obtain something like this for the differential equation matrix. So there's some Lorentz series basically. In addition, you have this factor x to the power r in front, and r can be a rational number. So if you have a canonical basis, there's often square roots in the basis. So typically r might be a half integer here. But in any case, once you do this, every integration up to some desired order in the line parameter can be performed straightforwardly. I think there was something wrong with the export here, but this should be a sum. So the idea is that if you integrate any term of this form, you just get a sum of terms that are again of a similar form, where you have x raised to some power and some logarithm raised to some power. And it's obvious that you can do this because if you do integration by parts, you can always reduce the power of the logarithm in your integration, and you just iterate that until your logarithm is gone. Yeah, but so in general, this all doesn't necessarily work because you might not have a canonical form, or your matrix valued 1 form, it's not a sum of d logs. And also more complicated kernels may appear, and you might not have studied sufficiently the iterated integrals that gives rise to. So in that case, you end up with these non-canonical systems. And so what I'll explain next is how you can solve those. So when you're in a non-canonical system, or really just a system that is not in canonical form, then the differential equations just take a very generic form where you have some factor of mass integrals depending on some number of external skills, and then there's the dimensional regulator. Now, well, again, we're interested in solving this along some contour because we're going to find series solutions. So basically, our differential equations, they combine to, well, they simplify to just some derivative on x, where x is the line parameter, and you use the chain rule to get this matrix AX. Now, one thing that we'll assume in the following is that this matrix AX has no poles in epsilon. Typically, I mean, many times when you derive differential equations, you will not find such poles. But if you do find them, one way of getting rid of them in most cases is just to add overall factors of epsilon to particular sectors. And then you obtain this form. So this requires a slight bit of manual work, but as far as I know, this is always possible. Then we also assume that the expansion of our mass integral starts at finite order, but that's of course not a very deep condition, because you can always redefine your mass integrals by including some overall power of epsilon to make it finite. So if you consider this expansion here, then then you end up with this set of differential equations given at the bottom. And so there's a homogeneous there's a homogeneous component given here by this AX0, and then you got this inhomogeneous component here, which comes from all the terms that are of lower order in epsilon. Now, once you start integrating, the idea is to start with the lowest orders in epsilon and start from subtopologies and then constantly integrate up. But one of the difficult things here is that some of the integrals are coupled, which means that, say, if you take a derivative on the integral I, it has a component of integral j, and when you take a derivative on j, it has a component of integral I. So the derivatives depend on each other. Now, so if you write a package that is supposed to solve these differential equations, in the generic case, you need some way to read off the integration sequence. And you also need to deal with these coupled integrals. So that's the next part that I'll explain. So essentially what you can do is that if you're, well, you can take your AX of 0 and you can interpret it as an adjacency matrix of a directed graph. And basically what you do is you add an edge if the derivative of integral I has a component of integral j, then you add an edge j goes to I. And then the next step is to look at this graph and you determine the strongly connected components of the graph. So these are the sets of vertices for which there's a directed path between every pair of vertices. And also in the conventions that I work with, then every vertex is connected to itself by the trivial path, which means that an integral by itself would form a connected component as well. So to just give that some visualization, I got this picture from Wikimedia. And what it shows is you start with a directed cyclic graph. So there's cycles in it. And then you compute the connected components. So those are the big blobs. So you see that in these blobs, every vertex can reach the other vertex by going along the directed path. Now, what is interesting is that you can compute a so-called condensation graph, which is basically the graph of the connected components. So you take all these blobs of the connected components, and then you basically make a flow from the connected components towards each other. And this gives you a graph that has no cycles. And so if you interpret this as the matrix of the differential equations, then basically what you're seeing here is the sequence in which you have to integrate things. So for example, this one, this blob goes to this blob here, which means that you should first integrate this blob before integrating this one. And the integration order is not unique necessarily from this, but you just have to make sure that whatever integration order you pick respects the ordering that you have here. So it's called the topological ordering that you need to compute. Right. So, and that's written out on this slide in a bit more detail, but it's a bit dense, so I will just skip over that. Now, so going back to our original system, we had this equation here. So we had this homogeneous component at some order in epsilon, and then we have the terms coming from the lower orders in epsilon. And now we consider some set of coupled integrals, and for convenience label those by G1, G2, etc. And then basically you get a system of differential equations of the same type, but now you're sure that what's in the homogeneous component are only the coupled integrals. Now, if you work that out explicitly, this inhomogeneous term has some rather long expression, which is just saying that everything that is not in everything in the derivative that is not coming from the homogeneous components is put in B, and then M is the matrix of is the original matrix, but restricted to the coupled integrals. So then basically you end up having to solve a system like, well, a set of differential equations like they are given here at the top. Now, this is of course rather standard material on how to solve something like this that I guess you learn in your undergrad. So the first thing you do when you have such a system is you solve the homogeneous part. And then usually you write the full solution using something like variation of parameters. Now the homogeneous part, one way to solve this is to take the system and first combine it into a higher order equation for one of the integrals. So here I wrote down a p-th order equation, assuming that there's the number of integrals in G is given by p. And then once you find p homogeneous solutions for GI, then well, you find these homogeneous solutions using what's called the Frobenius method and the method of reduction of order, which is also something standard, so I'll skip over it. And then basically you can solve for the remaining integrals Gj in terms of GI. So the more detailed steps can be found in my paper. Now, to just add a bit more details, so basically if you single out some integral, say G1, you can write down a factor of its derivatives. And basically then you can rewrite that factor of derivatives by basically a change of, well, just by a change of basis of the original integral. So all the derivatives of one of these coupled integrals can be essentially expressed by the remaining integrals. Yeah, and then the point is that we solve G1 using standard techniques like the Frobenius method and reduction of order. This will give you some kind of Wronskian matrix of homogeneous solutions. And this Wronskian matrix, you can then actually use to obtain a whole a matrix of solutions to your system here at the top. So if you define F to be M tilde inverse, where M tilde was this matrix here, then dF equals M of F. So it satisfies this original system. Now, then you have the inhomogeneous differential equations, which you have to solve. And yeah, again, so one way of doing that would be to use the method of variation of parameters. Now, something that slightly helps is to do what I do here on this slide, and basically consider a matrix solution, like a matrix solution to this inhomogeneous part. Let's find a particular solution like that. And well, if you work that out, you end up with this solution here at the bottom. And maybe in view of time, I won't really go into it that much, but the point is that you have this matrix G, and by summing over the columns, basically you've solved your system. Now, what is somewhat nice about this approach, I'm skipping some slides. What is nice about this approach is that if you look at the expansion in epsilon, then each order in epsilon, here indicated by the superscript, each expansion order in epsilon is given by this expression here on the right. And what you see is that this matrix F always stays constant. It's always the same. So you solve it once at epsilon order 0. And then these matrices B and E E is basically a matrix of indeterminate constants that you have to fix from boundary conditions. And then B is whatever comes from your inhomogeneous solutions. Now, if you do it this way, then basically at each order in epsilon, all you have to do is to do some matrix multiplications. Basically, you settle B, and B is completely composed out of whatever you've already computed. And then you simply do a matrix multiplication, you do an integration, which is very simple once you have series expansions because it's just a replacement rule, and then you do another matrix multiplication. And this is a really efficient way of solving these coupled systems, and it really helps when you consider things like the banana graphs. And instead, if you just applied variation parameters at each order in epsilon, you'd have to compute many determinants. So in particular, you'd have to compute p determinants of size p minus 1 times p minus 1. And yeah, that gets very heavy because a determinant is already heavy to compute, but now your determinant is made out of series solutions. So you're multiplying series after series after series, and this gets very difficult. So yeah, that's basically the underlying approach that is used in DiffExp for solving the differential equations. Now, every series solution has only a finite radius of convergence. So what you want to do is to concatenate the series solutions. And furthermore, each individual segment, you don't want to evaluate too close to the singularity. So one thing you can do is, for example, only evaluate series at 1/2 the distance to the nearest singularity, or 1/3. And then the convergence becomes a lot better. So I have made a nice picture here that kind of shows you how that segmentation works. So for example, you might have the following set of singularities. So there's one that is close to -1/10, and then there's singularities at 0, 4, and 16. Now, suppose that you're trying to go from the point 0 to the point 6, then how do you partition your line? Well, something that I haven't mentioned, but which is very important for this, is that well, your radius of convergence is of course determined by the distance to the nearest singularity. So if you're centering an expansion at 0, their radius of convergence will be basically limited by this singularity here. And if you're expanding around any regular point, then it's just the nearest singularity on the left or the right that determines your radius of convergence. So essentially what starts to happen is that your first expansion has a very small radius of convergence, but then the next one becomes a bit larger, and it becomes increasingly larger because there's quite a distance to bridge before you reach the new singularity, which here is drawn at 4. And then by picking your expansion points in a nice way, so those are the blue dots, you can always do it in such a way such that the matching between neighboring line segments is always done in such a way that the distance to the nearest singularity for the respective segments is 1/2. And the only exception is once you get close to a singularity, you usually have some overlap in the radius of convergence, so you can choose to match anywhere here. Now, then another aspect, so you see here that the expansion is centered at the singularity in order to get to the point 6. Now, typically what this means is that in your series solutions, you have logarithms and square roots. Now, these logarithms, they can appear from the integration of poles. So if you have, well, basically, whatever introduces a poles, at some point you have to integrate over it, and that will give you a log of x. There can also be square roots in a homogeneous solution, and this happens from the Frobenius method. So yeah, basically the Frobenius method is a way of solving homogeneous differential equations by making an ansatz. And this ansatz has an initial equation in it, which is a polynomial equation. And if that thing has a half integer root, then you will find square roots in your solutions. But the nice part about this is that these are very elementary functions. So both logarithms and square roots can of course be very easily analytically continued if you assign some I delta prescription to your line parameter. So for example, if log of x is the standard branch of your square root, which would correspond to having a plus I delta here, then you could express the branch where you have a minus I delta by introducing some theta function. So this theta m would be Heaviside theta of minus x. Now, you don't really want to carry around all those theta functions because your code would get slow. So then what you do is that if you evaluate at a negative point, you apply some replacement rules. So yeah, if your x has a negative minus I delta and you evaluate at the negative point, you simply give every logarithm a minus 2 pi I and every square root a minus. Now, of course, the way that you determine whether x should carry a plus I delta or a minus I delta, that comes from the Feynman prescription. So in typical planar cases, you would assign the Mandelstam variables plus I delta and the masses a minus I delta. And then you simply look at the line in which direction you're going. So if you're going in a positive s direction, for example, where s is a Mandelstam variable, you would want to give x a plus I delta. Right. Yeah, and that's basically how that works. And one caveat is that you should avoid crossing two singular regions at the same time. So for example, if you have Mandelstam variables s and t, then if you simultaneously go in the positive direction for s, but in the negative direction for t, then the two I delta prescriptions would clash. So you always want to basically separate out singular regions and cross one singular region at a time. Okay, so yeah, the beginning of the talk is rather dense. It's hard to make that any nicer, but now we can do some examples and then things there's some pictures and things become more straightforward. So yeah, these series solution methods. One thing that we applied them for was for the computation of Higgs jet integrals. So basically, these integrals, they were already considered by by Roberto Ponciani, Vittorio Del Duca, Jelte Frelesvik, Francesco Moriello, and Vladimir Smirnov. And at the time, they were computed using differential equations, but in a fully analytic way. And then Francesco came with a paper of and a way of solving these planar families using these series solutions. And later on, we repeated the same exercise for these non-planar integrals. Now, what is interesting about these kind of integrals is that well, they're very, very large. So if you do an IBP reduction and you go to the default basis, you would have you would have 1 gigabyte of coefficients of your IPP reduction. Now, by basically doing the whole analytic simplification of the differential equations, deriving a canonical form for many of the sectors, you can greatly bring it down. And I think in the end, the differential equations that we had for such a family were of the order of around 10 megabyte, and the same for family G. And now this family has some elliptic top sectors, and the same for family G. It also has some elliptic top sectors, which makes it very hard to compute these. But yeah, using some private codes that we had at the time, so not just mine, multiple people in our collaboration had codes to compute these things. We managed to, basically obtain some very nice three-dimensional graphs and compute these integrals in a way that it hadn't been possible before. And so it's nice to see that kind of an approach that is somewhat blind to the underlying differential equations can still be very, blind to the underlying integrals, and that just looks at the differential equations and just naively expands them and solves them, can actually give some really good results. So these plots, they can be derived in, let's say, half a day on a laptop with 10,000 points and 25 digits precision. So that's roughly the orders of magnitude we're talking about. Right, so I just wanted to get that one out there because it's a multi-skill example. But now, to be more in line with the spirit of this conference, we're going to look at these banana graphs, which are tricky to compute because, especially in the unequal mass case, they are not known to evaluate to some EMPLs. It's something more complicated is necessary. Now, first we'll look at the equal mass case. So we just define this banana graph. Many people have seen it before. And then you have a set of differential equations given here at the bottom, which is actually very small. I mean, this is a very simple system of differential equations. And now the way that I wrote this is that I normalized out the mass dependence and work with p squared over m squared, but that's equivalent to putting m equal 1 and just working with p squared. Now, one thing that's slightly tricky for this family is you have to compute boundary conditions. So I won't go through the whole calculation, but essentially you can use the program ASI to get regions for the expansion by regions approach. You can then manually parametrically integrate all the contributions from all the different regions, and basically you can obtain some boundary conditions. And this is done. So this line parameter, it parameterizes the limit where the mass goes to 0. And so what's very nice about this is that your banana graph is essentially given in closed form in epsilon in leading order going to this limit. And then, so next I will show how you can take this boundary point and then obtain results for any values of p squared using this package. So, well, the typical way that you use the package is you'll load some configuration. So you'll tell the package where the matrices are, and you'll say what is the working position, etc. Then you'll prepare the boundary conditions into a format that the package can use. And then there's two functions. One is called integrate system, and it just gives you the series solution. And the other function is called transport to, and it takes some set of boundary conditions and transports them anywhere else. And this also does automatically the analytic continuation. The only thing is that you'll have to give the I delta prescriptions to this first function. So what that looks like in practice is you load DiffExp, you load the configuration, you plug in the boundary conditions, and then you run transport to. So I'm going a bit fast in view of time. Yeah, and then after running those functions, there's one additional function to piecewise, and it basically puts together all the expansions, and you can then plot them out. So here you have a nice graph of the banana graph around the threshold where p squared is 16. Now, to give some timings also to compare a bit to the other methods, because there were many talks on numerical methods earlier dealing with the numerical evaluation of EMPLs through Q expansions or implemented in GNAC. So if you go from p squared is minus infinity to p squared is 30 at 25 digits, with this code, it takes about 90 seconds, and you get the banana graphs up to epsilon third. And that's all the mass integrals, and that's on a single core. Now, if you do this at 100 digits, it takes about 20 minutes. And yeah, then we're still computing up to epsilon order 3. Now, I thought to compare with one of the previous talks, if you go to the point p squared is minus 100, well, that's very close to where we computed the asymptotic boundary condition. So it becomes actually very fast. So in 50 seconds, you can get 100 digits out. And in 2.5 minutes, you can go all the way to epsilon order 3 for the banana graph with 100 digits. I'm just going to go a bit fast and say that we also, well, using DiffExp, you can also compute the unequal mass case, which is difficult using many other approaches. Well, and it's also difficult for the Mathematica package because there's 11 coupled integrals. And what happens is that basically the series coefficients of the expansions, they blow up at intermediate stages and become very large. So you have to put a really large working precision, more than 1,000 digits. But then you can get it to work. And for example, here I provide 55 digits of the basis integral B11. So that's the undotted integral in some point where the masses are different. And b squared is 50, so it's above threshold. So we also did the analytic continuation. And if you do this, then this point can be obtained in about 23 minutes. So probably could be improved even further in the future, but yeah, that's what we have now. Then I also want to show the for loop banana graph. And there's an index missing here, but it's a for loop banana graph with 5 propagators, and we picked the following basis. Now, you briefly saw in one of my previous slides that, well, using this approach of expansion by regions gives many different regions, and you have all these gamma functions that you have to compute from the parametric integral. So that's kind of complicated. So an alternative approach, which is quite interesting, is that you can use the differential equations purely by themselves to determine the integrals. And the only input you need is that you know where the singularities are and which singularities are non-physical and should disappear. So this follows basically an approach of this paper here, where this was first done in the context of differential equations, and then in the context of series expansions, this was also done by these people here, and there's a name missing here. More yellow should also be on there. So right, so if you do this, basically you can first find the general solution around t0, and that gives you some logarithms which you which should not be there, because this integral is finite and it should be well behaved as you put p squared to 0, because you have masses on all the propagators. So this gives you some set of equations that you can use to fix indeterminate coefficients in your general solution. Now you transport and you center an expansion at t is 1, and again you'll find logarithms which shouldn't be there, and you repeat it the final time, and then you get rid of another non-physical singularity at t is 9. And so then the only physical singularity that remains is at t is 25, and all the coefficients are then fixed. And so once all these coefficients are fixed, now you immediately have results at t is 0, and you can of course transport them to any other point. So here I have some results for the for loop banana at t is 50. Now I just truncated these numbers for convenience, but for the presentation here, but in principle you can also go to very high precision for this. So the calculation that I ran it twice at different expansion orders, and it seemed to give an error of 10 to the minus 70. So yeah, you can go to very high precision, and that is really all I have to say on the example. So yeah, in Ruth's talk earlier this week, there was also some mentioning of cut integrals, and I won't really go over them, but what's quite interesting for if you have an analytic eye is that you can also compute boundary conditions for cut integrals, use the same differential equations to transport them anywhere. And this is quite nice because cut integrals are generally quite difficult to compute fully analytically. So this way you can compute them numerically and transport boundary conditions to various points. So yeah, then just to conclude on the story, series expansion methods provide a quite efficient way to evaluate Feynman integrals. They allow for obtaining high precision numerical results, and also for all kinds of integrals, so also those that are beyond the elliptic type. Because in a sense, they're blind to whatever the geometry is of the integrals. Yeah, and then lastly, we now have this package that I released that hopefully will make it easier for people to apply these methods in general. Yeah, and that's all. So thank you for listening.
Thank you. Let's all take a couple of seconds to unmute ourselves. And I see there's already one question by David.
Yes, so thank you for this very impressive presentation. As you might expect, I'm interested in the for loop sunrise diagram, or banana diagram as you call it. There you only had 2 pseudo thresholds at 1 and 9. And the unequal mass case, I think you would have rather a large number. I think it's when the external momentum square is equal to the square of any signed combination of the masses. So how would your performance time change if you, you know, your code would presumably be the same, but you'd have to handle a large number of pseudo thresholds.
Yeah, that's partly true, but you could first compute the equal mass case and use those as boundary conditions for the unequal mass case. And so you could first stick to the equal mass case and just require the absence of these simple pseudo thresholds. Then you have completely computed the equal mass integrals. Now, if you go to the unequal mass system, well, you can take the boundary conditions anywhere. So in particular, for the unequal mass system, you can take as boundary conditions the equal mass system. So you would have also fixed the unequal mass system from just those.
I'm sorry, I don't understand that. And the equal mass system, you have one parameter, p squared over m squared, and the unequal mass ones, you have a large number.
Okay, that is, yes, that is true. But if you go to a point where the masses are equal, you have essentially also one parameter. So yeah, so I mean, if you think of maybe if you think of a how do I explain that? Well, essentially, you can pick any point, any point as a boundary point in phase space. So you can go from any point A to any point B. And so that point A can just be a point where the masses happen to be equal, and that point you determine. So your number of mass integrals goes up, but essentially what you're doing is you know the symmetry of the mass integrals. You know that in that point, all those top mass integrals, they're all equal to each other. So you just set them equal to what it should be in the equal mass case, and yeah, then it just works.
Thank you. So instead of moving on a line, you move around in a multi-dimensional space.
Yeah, exactly. So yeah, so first you're just on this line where the masses are equal. There you fix everything, and now you can just take a line that goes into the multi-dimensional space, and yeah, you can just integrate in that multi-dimensional space.
Thank you very much.
We have another question by Roman.
I have a question and I have a comment.
Okay.
The question is the following. If you increase the precision, how does the time scales? Of course, it's polynomial, okay, but the question is, what is the power?
I don't know. I've never tried to really do this, but yeah, if you go to high enough, so there's two things. You can increase the, of course, the working precision of the individual coefficients, and then you can increase the expansion order of the series.
Working precision one, and then what else? Then you have to calculate more terms of expansion, right?
Yes.
Each term of expansion, it involves probably, in your approach, involves some linear combination of all previous terms, right? So this linear, the size of this linear combination also grows with the number of coefficients. This is 2, okay? So, and then I come to my comment or remark. Actually, we tried, in our paper, we tried to overcome this cubic growth of the precision, of the complexity. Because if you get rid of denominators, you can obtain a finite order recurrence relation between the coefficients of the power series. This what we fought for, to have as many digits as possible with a minimal time. This was one improvement that we were trying to do. The other thing is that we calculated only expansion near singular points. There is no necessity to calculate expansion near regular points, although it might seem differently, but you know, you can use a Möbius transformation to distribute
but
neighboring
the
point.
Möbius transformations are not enough in the general case, I think.
Because, is enough. Why?
Well, I have also implemented Möbius transformations in the package. Okay, so one problem is there are complex singularities in general, and so what do you do then? Yeah, how do you Möbius transform those? So that's one issue. And yeah, and then I think a second issue is that if you just use the Möbius transformations, at least in my experiment, so if you only expand the singularities and use Möbius transformations, then at the points where you're matching, it might still be very poor convergence for one of the series. So in principle, yeah. So in the approach that the package is using, you're taking the boundary conditions and you're going from one segment to the other. But what can happen with these Möbius transformations is that although everything is within the radius of convergence, one is very, very close to the radius of convergence, and the other one is close to the origin.
But my point, that's my point is the following: that Möbius transformation should be used if you want the most effective implementation, because you can also use expansion near regular points. Regular points is a trivial example of singular point, right? So all tools that you have for singular points, they work also for regular points. So there is nothing new. So you have to be as economic as you can, and of course, as you said, the convergence rate, you can trade the convergence rate with a number of expansions that you need to make to pass from one point to another. This is a trade, so to say.
Yeah, exactly. And this is a trade-off. And I mean, right now, just by trial and error, it seems that when you subdivide in such a way that you never go beyond half the radius of convergence or 1/3, those two options seem to be quite well. That works quite well. If you go even closer and you add even more expansion points, then definitely that seems to not be as fast as just increasing the expansion order. But on the other hand, just expanding at singular points, in the examples that I looked at, the convergence was very slow. And of course, like you say, things grow very badly as you increase the expansion order. So then it might really help to just expand at the regular points.
No, I said differently. I said that we specifically took care of this, so that this convergence, I mean the timing.
Yeah, but in your approach, that's a special, that's a more special case. It doesn't work in general.
Not to
maybe in view of time, we can continue the discussion after the next talk. There we have 45 minutes for further discussions and further questions.
Yeah.
Okay. So thanks again. And the next talk will be by Albrecht Klemm. So it's a pleasure to have Albrecht Klemm talking about the analytic structure of the all-loop banana amplitudes. Please go ahead.
Okay, thank you very much for having me in this conference. And this is a work which I have done in collaboration with all students from Bonn, which are indeed very good. And it is based on two papers, one that we released in December last year, and one which is very recent. And now I have to. So let me give you a short introduction. I fear that you know everything, and but we consider a Feynman representation of the graph contribution in terms of an integral over graph polynomials, and it is so that the graph polynomial in the numerator is actually independent of the physical parameter, which are the momenta and the masses. And then we have here this measure, which turns out to be a measure on Pn, and we have a region that I describe in a second. So moreover, D is the dimension, and N is the number of edges or propagators, and nu I is their multiplicities. And then we introduce a parameter omega, which is basically the sum over these multiplicities, minus L, which is the loop order, the number of loops. And of course, if the graph has an Euler number, then you can give the vertices in terms of the data that I have mentioned before. So let me come to this integration domain. It's basically, as I said, it's in Pn minus 1, and it's in homogeneous coordinates written here, and all the xi are positive real numbers. And that is a chain integral because we integrate over an open domain. But then on the other hand, the measure we know very well from Calabi-Yau period integrals. it is basically the standard measure on Pn-1. And so I only will calculate one graph, but of course, generically you need dimensional regularization, and you evaluate therefore in d minus 2 epsilon dimensions. And it is, so to say, well known by work of, very important work, that all this epsilon expansion will be twisted periods, or potentially actually general Calabi-Yau motifs, which are realizes minimally in L-1 dimensions. And I want to give now a very concrete example that has been featured, of course, before in the talks, namely a very simple series of such Feynman amplitudes in 2 dimensions. And this is, so to say, the Goldilocks case, because in 2 dimensions, the exponent of the graph polynomial in the numerator will be 0, and the one in the denominator will be 1. So in this case, we get a very fairly standard chain integral on a Calabi-Yau background that we can eventually discuss with methods that come from mirror symmetry. And that is more or less what I want to do. So, so this is this L-loop bananagram. You have just L plus 1 masses, and you have just one external momentum. And then, of course, this is a planar graph. And then, as I said, the exponents of the graph polynomials are so that you have only a polynomial in the denominator and this measure in the numerator. And it's convenient to sort of introduce dimensionless quantities. So you introduce a scale mu so that the t and the psi become dimensionless. And then you look careful at the numerator, and you see there a polynomial, Laurent polynomial. I mean, this piece is a Laurent polynomial. And this is what I call P delta L. And this Newton polytop of the Laurent polynomial is actually reflexive in the canonical rank L lattice. And here there are some figures for the first loops. So yeah, so this is for L equal 1, 2, and 3. And you see, it's not so bad. They are all reflexive polyhedra. And that one is, for instance, the blow up of P2 in 3 points. And that is a K3 polyhedron. And some things look very good for mirror symmetry, because we are used to the situation very much in work that we have done on Calabi-Yau manifolds. So basically, since this polyhedra is reflexive, there is a dual reflexive polyhedra. Both of them contain just one inner point, like this is the decisive feature here of this polyhedra. And then you can take a Calabi-Yau and the mirror Calabi-Yau as the section of the anticanonical bundle in the toric projective space, which is canonically defined by this reflexive polyhedra. This is, can be read in books of Cox and so on. And then we have Butterev mirror symmetry. And we get 2 manifolds, and the lower index always indicates the dimension of this manifold. So it's L-1, and they are both Calabi-Yau, and that is the mirror Calabi-Yau. So I use this joke that Candelas make, that W is mirror to M. And these are my 2 manifolds. And now you can look at the, one of these things is not work. Oops. I have a little bit problems with my keyboard. That is stupid. It is reacting slowly, but it's reacting. Okay, good. So, so the Feynman integral itself is, as I said, is a relative period or a chain integral over this real L-1 cycle that I have shown you. And, and given that fact, this is in principle straightforward to calculate this. And this was performed for L smaller than 3, also in the non-equal mass cases in 1 and for L equal 4 in 2. And so there are, from our point of view, various, straightforward steps. So you first determine the flat Gauss-Manning connection on ML minus 1, and then you solve for the periods where this gamma k is a basis of the middle cohomology of this manifold, and omega is the unique Calabi-Yau n form, or L minus 1 form in this case, which just exists on any Calabi-Yau space. So the first task is best done by starting with the Gelfand-Kapronoff-Selewinsky differential system, and then deriving the Picard-Fuchs differential D model from it. And what is a Picard-Fuchs differential D model? It's a complete system of linear differential operators that annihilate these periods, but they have no further solution. And it can be sort of, with a little work, it can be derived from it. And once you have this D model, you can, of course, easily calculate the Feynman graph everywhere in its moduli space. By this methods that we heard before, basically you expand the series and you design enough region of convergence, preferably near the singularities, and then you have an overlap region and you cover the whole physical moduli space. So if you solve this differential equation, of course, this leads first to the local Frobenius spaces, which I call warp psi hat. And this gives you a number of solution, which I call HL minus 1. And now you have to determine the linear combination, which correspond actually to the geometrical integrals, in particular to the Feynman integral. And you can also ask the question for the Calabi-Yau. Then you want to have the integrals which correspond to actually elements in the middle homology of the Calabi-Yau. And that can be actually easily achieved. I don't know whether you know that, but this is achieved by the gamma class formalism at the mum point. And I will use this also for the Feynman graph later. So then you commute the deformation modulus of the inner point. I mean, these are reflexive polyhedron. They have a unique inner point. So this ideal that you have defined before. And then you do this at the mum point. This is most convenient in special linear homogeneous coordinates, which are also fixed by mirror symmetry. And then you get the inhomogeneous equation that were also mentioned before. And we got them in the first work, well, in this form. And here there's where constant times logs maximally. But this is not a general feature. I mean, they still look simple, but there could be Z-dependent polynomials here and polynomials that depends on the log here. But you can determine, and we have determined this, for instance, for the for loop non-equal mass banana graph. It's not a big problem, so you can do that. So now you have this homogeneous solution to the system, which are in one-to-one correspondence to the periods on the Calabi-Yau, and they can be linear combined to get the maximal cut integral. And if you add the single inhomogeneous solution, you can write now the Feynman graph. So we have this basis here. This now runs from k equals 0 to L minus 1. So you get everywhere Frobenius spaces. And the Feynman graph will be a linear combination where these constants that I call lambda Lk are generic constants in C that you, for instance, can determine by this method of analytic continuation that we just heard. So that is, so to say, characterize the Feynman graph in all regions of the moduli space, and is a good way of solving these things. So for L equal 2, there were similar solutions found using Griffith's reduction method by Spencer Bloch and Matt Kerr and Pierre van Hove. But I have to say there are some shortcomings in this geometric description, and you can easily see that. I mean, if you think about this polyhedron, they were growing very fast is the dimension, in particular the vertices were growing very fast. So if you think a little bit about it, then you see that the dimension of the deformation space, which are, so to say, all the vertices at the edges of the polyhedron where I have to put small m values, which depend in some complicated way on the physical m's, this grows with L squared, and it grows, of course, much faster than the number of physical parameters, which in this case only grows with L plus 1. And if you think about the total cohomology of this space defined by this reflexive polyhedra, then you will find that the relevant periods are only a very tiny piece of the middle cohomology of this Calabi-Yau manifold. And therefore, the derivation of the physical relevant periods becomes more and more cumbersome. And another problem that I want to solve in this talk is that these coefficients could be only determined approximately by a numerical analytic continuation. But in this talk, we will do much better. So to overcome these problems that I mentioned, we propose a better Calabi-Yau motif for the banana graph and new gamma hat classes. And these are inspired from homological mirror symmetry and will solve the problem very, very beautifully, I think. So what is the better Calabi-Yau motif? Well, I mean, if you look at the Feynman graph, then you look at the mirror of the Feynman graph. This I call it WL-1. And this is embedded in the Fano variety. And what I want to propose is basically a Calabi-Yau, which is written in this form. So what is it? It is a bunch of P1s, actually a product of L plus 1 P1s. And in this P1s, you have one hypersurface constraint, which is of degree 1 in every coordinate of the P1. And then a second one, which is also of degree 1 in every coordinate of the P1. And by the adjunction formula, I will easily see that it's a Calabi-Yau. And moreover, it is embedded into a Fano variety, which has positive Chern class, which is obtained by just leaving away one of these constraints. And this I will call in the talk FL. So this WL are complete intersection Calabi-Yaus, as we call them. And the way that they are described, I have just explained you, just that I want to say this complete ambient space, which is this product of P1s, I call AL plus 1. And that is also the ambient space of the Fano variety, which is the degree 1 constraint in this space. So then there is some amazing beauty to this picture, because you see every mass corresponds precisely to one of these rational curves in this Calabi-Yau. And if you start thinking about it, then you realize there is a very nice relation between the volumes, or we in mirror symmetry say quantum volumes for a reason that become clear immediately, with the masses of this Feynman graph. So it is that you have all this L plus 1 rational curves, which are actually visible as P1s. And their quantum volume, what is it? So you take the symplectic form, which any Calabi-Yau is scalar, so you have symplectic form. And in mirror symmetry, we make this complex, so we add the B field. But actually, this real part of this, note there is a 2 pi I here, is simply the area of this P1. And the area of this P1 is just the logarithm of the mass squared over the momentum squared. And we will introduce canonical coordinates for that, which are called ZK. And now this is a good picture at this high energy, super high energy region of this Feynman graph. And this thing becomes 0, and then the logs become, and then these area become infinite infinite. And away from this area, there are quantum correction, which we call instanton correction, and they are going with e to the exponential of this volume. So they are suppressed in this limit. But nevertheless, you can actually calculate them, and that was done in a paper by with Yau, Tyson, and Hosono a couple of years ago, actually. And this has a very easy GKC system, much easier than the GKC system of the reflexive polyhedra. And if you solve this GKC system, of course, you get all these exponentially suppressed terms. and you get the full Feynman graph integrals. And also now we have no redundant parameters as we had before. We have just the parameters which corresponds to the volumes of this P1. And in mirror, after mirror duality, I call them ZK. So K really runs just from 1 to L plus 1. And then there is a very nice vibration structure in this whole picture, because think what is the elliptic curve? So the elliptic curve is, of course, one complex dimensional. So you take a 3 complex dimensional space, which is 3 P1s, and you put 2 hypersurface, then you get the elliptic curve. It's, of course, again, a Calabi-Yau, so it's an elliptic curve. And that is associated to the 2-loop graph. And then the K3, which is associated to the 3-loop graph, is now fibered in 4 ways by this elliptic curve, because over every P1 that you can put here, you have this figure here. And of course, it doesn't matter which curve you put. You get a K3, which is in 3 ways fibered by an elliptic curve. That means you have for this K3, 3 contractions to a P1 in 4 different ways. So 4 contractions. And if you go on, then you see that the Calabi-Yau threefold is now fibered in 5 ways over the P1s. I mean, so the Calabi-Yau threefold has 5 K3 fibration structures. Each of these K3 has 4 elliptic fibration structures and so on. So this looks like a very complicated vibration structure, but it just reflects the fact that you can send the masses in arbitrary order to infinity and obtain a lower loop graph. And the lower loop graph is obtained by the lower dimensional Calabi-Yau. And of course, since the masses are the volume of the bases, you see that this corresponds to this vibration. So in this limits, the base decompactifies, and this basically exponentially suppresses the corresponding instantons. And also, if you say that the full graph, as I will argue then in a second, is described by a general GKC system, you can get in many, many ways to your favorite elliptic dialogarithm or whatever in every fiber. So we can also see that the intersection calculation done for this gamma class, we have to do them anyway, reveals that this Oguisu criterion for the vibration structure of Calabi-Yau is fulfilled. So now let me get, so to say, a first view on the analytic structure that I really want to discuss. So we have here the equal mass case for simplicity, but in fact, it will not make a big difference at the end because we can also calculate this analytic continuation constants for the non-equal mass case, as you will see in a second. So what is this moduli space? The moduli space for the 1 parameter Calabi-Yau is just a P1. And there are a couple of points missing, and these points we have seen before. For instance, there was this 25 for the 4-loop graph, and then there was this 9 and so on. These are the lower order singularities, but it is like this, that there are 2 very important points. This is this point of maximal unipotent monodromy, where, as I said, the volumes of all the P1s are infinite. And then there's the point S equal infinity, where people have over many years worked out a very beautiful description of this Feynman graph in terms of Bessel function. And then for the actual integral that I was considering, of course, you can consider also other period integrals, then this conifolds will be also of relevance. But for the actual periods, for the actual integral I'm considering, the radius of convergence is limited by this last conifold point. And then there are, so to say, less important points. I would say there is a point where this thing becomes pure torsion. Then you can actually express even the Feynman graph in this. The Feynman graph becomes pure torsion in the homology of the Calabi-Yau, and then you can get some special values for this fiber. And then there are also the fibers where S is an algebraic numbers. This were found by Candelas recently, and there the Hasse-Weil Zeta function splits, and you can make also some exact calculations. So, so as I said, to simplify the presentation, I restricted to the equal mass cases, but later on we will see that there are many things that I can see also about the general case, say about the general case. So, so this diagonal differential D model, I mean, it's just one operator, has order L. So for instance, for the for loop graph, it would be this differential operator. And here from the symbol of this differential operator, you see again the conifold discriminants. And this is just an example. And then the inhomogeneous term is, so to say, universally given by L plus 1 factorial. In this case, it's 120 factorial. So let me, so to say, now go to the important singular points. So there is this Bessel points, and over the years, the people have expressed the amplitude in terms of a Bessel function integral. So you cannot express it exactly as a series, but you can do a very good thing. I mean, you can sort of say express it in terms of a single integral over a bunch of Bessel functions. And these Bessel functions contain T, which is 1 over S, and they contain also this dimensionless mass parameter. But as I said, the radius of convergence of this expression is limited by the last conifold. And in general, it would be limited by this divisor here where the masses go in. And it's also very simple to get this DL because you take just the symmetric product, the L symmetric product of this Bessel function operator, which is trivial, and then you take 2 times the Borel transformation, and you get this operator that I have showed you here. So that's a general feature. And now let me talk about the conifold. So at the conifold, in our case, this is only singular at this last conifold, which is at S equal 1 over L squared. And what happens here, there is a single cycle in the middle cohomology of my Calabi-Yau, which vanishes. And according to Lefschetz, that gives rise to a reflection monodromy if L is odd, which is really a square root cut, or a logarithmic cut, which is called a symplectic reflection in the speech of these people, or a shift if L is E. So now by homological mirror symmetry, I can actually, I will be actually able to determine the homology of this vanishing cycle exactly in terms of the gamma class of the structure sheaf on BW. And you will see this is very completely explicit in terms of beautiful Zeta functions and so on. And this fixes actually the Frobenius constant exactly, which in turn specify the conifold monodromy in this Frobenius spaces. And in the path of the analytic continuation that we chosen here, this conifold cycle will actually be exactly the imaginary part of the Feynman amplitude once you go around this conifold. So, so then there is another very interesting point, as I mentioned. I mean, there was the Bessel function, the conifold. Then there's this point of maximal unipotent monodromy, and that is S equals 0. So that is, you can also say what it is in general. It's not very complicated. In general, it's a normal crossing point of divisors, which are given by these masses. And it's also a point. It's not a divisor because these L minus 1 divisors meet here, and then in the L plus 1 dimensional moduli space, it's a point. And what happens here, the monodromy matrices MI, so why it's called maximal unipotent, they fulfill an equation when you take this monodromy and subtract 1 and take it to the power L plus 1, then it's 0. But what means maximal is that it doesn't happen for any lower power for all the matrices. That is what maximal unipotent means. And according to Wilfried Schmidt, this maximal unipotent behavior is caused by a hierarchical structure of degenerating cycle. So there will be logs and higher logs and so on, and they correspond to degenerating cycles. And that's exactly what happens here. And at the mirror dual point in the complexified Kähler moduli space, I call this complexified because we had the Kähler form, we integrated to get the volume of the curve, but then we had this B field. All the rational curves are big. And in this resulting classical geometry, we formulate a new gamma class conjecture for the Fano ambient space, which exactly captures now also the real part of the Fano space. So let me give a couple of small comments about these fibers with special evaluations. So there are fibers where the cohomology of the Calabi-Yau does something special. As I said already, as S equal 1, then the Feynman graph is pure torsion in the cohomology, and you can actually make beautiful, find beautiful values for that. And that has been done, I think, for up to L equals 6 or so. These are usually L function values of Hecke eigenforms of a certain of weight L. And then there are these rank 2 attractor points. They exist, so to say, we don't know, but they exist according to the analysis of Candelas only for L equal 4. And here what happens is that the Hasse-Weil Zeta function of the Calabi-Yau factorizes. So it factorizes into 2 terms, and you see this coefficients A, B. And here you see, of course, this is just the Hasse-Weil Zeta function of an elliptic curve. And this is the Hasse-Weil Zeta function, which gives weight 4 modular form. And you can find these modular forms easily. I mean, basically, there is a method, periodic analysis of the periods. And this PP are Fourier coefficients of a weight 4 and weight 2. This is for the elliptic curve, of course, and weight 4 Hecke eigenform, which is given here. And that was found by Candelas, Elmy, van Straten. And then you can actually calculate the periods and the quasi-periods of these forms. That's not difficult. It had actually been done in the master thesis of my student, and apparently also independent by Broadhurst, which in addition had a very nice feature that he also, I mean, that would determine all the periods for the maximal cut integral, but he had also, as I saw yesterday, a very nice method to get the full Feynman. But anyway, the master thesis of Kilian is super good and is also worth to be cited. So let me focus on the points which are really important, which are really singular. So now we follow this paper that I mentioned at the beginning that we wrote in '93, and we construct the Frobenius solution at this mum point. And there is a, so to say, a technical tool which is called the Frobenius cone, which is dual to the Kähler cone. And I should have stressed one thing very much. I mean, what I want to calculate is the vertical cohomology of this Calabi-Yau. I have stressed it in my slide, but not in saying. So we want to calculate the vertical cohomology of the Calabi-Yau. That is the one which is so small, and that is the one which is good, and that is the Calabi-Yau motive we are after. So this vertical cohomology is, of course, just I mean, at lowest dimension is based on this P1s that you see in the Calabi-Yau. And the Mori cone will be L+1 Mori cones, and they represent these curves. I mean, this P1s. And this Mori cone is given by this expression here. So it's here is -1, -1. This basically comes from the constraint. And then there are 2 1s which wander out until they are here, until when you have L+1. And then from that, you obtain a generalized Gelfand-Kapranov-Selewinsky system that we already did in this paper with Yau. And using the Frobenius deformation method, or now is sometimes called in this context Giventhal's I function, because he has proved it on the mirror side, we can write down this expression here. And this expression, you see, has a deformation parameter, which I call epsilon, or rather L+1 deformation parameters, which I call epsilon underlined. Here should be also underlined. And from that, you can get all the solutions. So basically, you realize that these Mori cone generators give you certain factorials, because this is a generalized hypergeometric function. So you see something like Pochhammer symbols, and they are given here. And then the epsilon deformation is done as usual. You just promote all the factorials to gamma function, and you deform all the generally all integers to epsilon+1, and therefore you get this also like here. And then you can immediately get all solution by just taking derivative with respect to epsilon. But let me first say what is at the point of maximal unipotent monodromy, there is a unique holomorphic solution that's given just by taking no derivatives, just by setting epsilon to 0, and that is written down here. And this ZK is just this S parameter times this dimensional mass parameters. And then, as I said, all the other elements of the Frobenius spaces can be taken just by taking derivatives. But you have, of course, you cannot take infinitely many derivatives because this solution system is finite. It's like the primitive cohomology of this Calabi-Yau. And which precise combination will lead to a solution is actually determined by the intersection number or by the showering of the intersection number in the primitive cohomology of W. And it's very concrete. You can basically immediately construct all the solutions at this point. And what is very important here, the dimension of the primitive cohomology, vertical cohomology of VW maps to the primitive middle horizontal homology of the mirror. And these are the ones which determine the solutions, this k-ordered logarithmic solution. And what is, of course, nice is that this primitive cohomology doesn't grow so much. So when you ask yourself how many logarithmic solution with log to the k I get, you just look here and that's what you get. So this is the number of the primitive cohomology, and this is also the number of solutions that you expect in each log order. So now I have described how you get the basis. It's straightforward. You can do it to very high precision, of course. They converge very nice until this next conifold. And now the statement is that this banana diagram is a linear combination of these Frobenius spaces. And I have to know which, because otherwise I cannot do too much. And now we have a statement which, so to say, in the paper we have just formulated that statement, but since Monday, I have received many mails from Iritani, which is a world expert on these gamma classes, and I think is now more or less a theorem. So the point is that these lambdas that I have here, which are, so to say, tell me of how I express my basis for the actual Feynman graph in this Frobenius spaces that I can quickly construct, is that this lambda are given by the following generating series. So it's basically that lambda L is x to the L. I mean, this is a generating series, and here you expand the gamma functions, and this is the Euler-Maccheroni constant. This is called, so to say, the regularized gamma function, because you don't want to see all these Euler-Maccheroni constants. And then you expand it, and that gives you these coefficients with, which are coming with the holomorphic solution. Then you ask yourself what comes with the first logarithmic, the second logarithmic, and the third logarithmic. And the answer is, again, very simple in this theorem. It's just given in the following way. And then the vanishing cycle at the conifold, which is, so to say, the integral over an S3. So nu has topology of an S3 and gives this a square root cut in the even case and the shift log in the odd case. This is given just by the imaginary part of these lambdas, so generated. So it's also completely fixed. What is the vanishing cycle at this point? So let me give you an example that you can see. I mean, now we have, so to say, we have this omega. So this goes without any log. This goes with a single log. This goes with a double log. This goes with a triple log. This goes with a quadruple log. And you ask yourself, what linear combination do I have to take in a certain normalization that you have to specify a little bit more carefully? You can read this in the paper. I mean, you have to set certain things to 1. And so what you get is exactly this coefficient. So you have, for instance, for the 5-loop graph, you have to take minus 288 sigma 5 plus 144 sigma 2. I also put the pi into sigma because it reads nicer. And then sigma 3 and so on and so forth. And if you want to have the leading logs of the Feynman graph in the high energy expansion, you just look at this. So this is true for all loops. So you can do this for actually, I mean, we have checked this because once you have, you know the form, you can check this to hundreds or even thousands digits that is true. And we check this up to loop order 14. It's always the right, I mean, this is just the right expression, and it has to be the right expression because I claim I can prove it. So now the idea to prove this theorem or whatever it is uses this gamma class, and it provides also an immediate generalization for the L-loop banana graph with arbitrary masses. So let's take, then you have a second index. So basically this counts the number of loops, and this counts the number of elements that have that many loops. And the number of elements that have that many roots is logs is just given by the primitive cohomology of L minus 1, which of course I have already given. And now this linear combination look a little bit more complicated. You have now here this number of solution which correspond to the primitive cohomology of BW minus L, and you have to find all these L's. And I can tell you that I can find this L's just the same way. You will see if I turn to the proof of this statement. And then you see, okay, I mean, for 4 loops, you get the same, of course, the mixture to the Feynman graph of the unique holomorphic solution is still given like that. But then the others, they split. And why they split so symmetric? Because this thing is so symmetrically fibered. So when you put various of these t's to infinity, you get the same subleading Calabi-Yau, and the coefficients can be also calculated. So let me come to the idea of the proof using this gamma class. So essentially, it's a calculation in the vertical homology of VW and the Fano variety FL, I should have written. So like here. This is just the dimension of these guys. So basically, we guessed first. I mean, the complicated part was to guess the Fano variety, the gamma class for the Fano variety. And I first guessed it. And then, as I said, Iritani got very excited and wrote many mails and said, this is the right thing to do. And I will tell you what is the right thing to do. So basically, what you have is now you take the mirror map. And the mirror map is basically just a single logarithmic solution divided by the holomorphic solution. And that is precisely what gives you the quantum volume of each of these P1s. And then you take the symplectic form. I mean, this is maybe hard to distinguish from this W, but you take the symplectic form either of the manifold or the Fano. I mean, either of the Calabi-Yau or the Fano. I call it in the same way because not to clutter the notation, but they are both, of course, scalar manifolds. So you have to certainly have a symplectic form. And then you expand, then you define for a rank S, a rank N sheaf S, you define the regularized gamma class. I mean, this was done first by Kazakov, Kontsevich, and Pantev, and then later Iritani, Goldachev, and Galkin, and even in our paper with Yau, we had already some ideas how this derivative with respect to gamma give actually rise to these coefficients. So then, according to Seidel, he tells you that this vanishing cycle of the conifold is just this gamma class integrated over the Calabi-Yau. Okay, so that's what it is. So then the other thing, and that's, as I said, we first have guessed it, but then Iritani has said it's not in the literature, but it's not close to something that he can prove. That is this one. So, then when you know that, then the rest of the thing is just standard intersection calculus on this Calabi-Yau BW minus 1, or FL of the Fano variety, and that's really easy. So you have the adjunction formula. So you have basically the tangent bundle and the normal bundle, and the normal bundle is squared because you have 2 constraints of 1, 1, 1, 1, 1, and then you take the degree k coefficients of this expansion, and then you get the Chern class of VW. So that's easy enough. And then, of course, the hyperplane class in each of these P1s fulfills H2 equals 0 because 2 hyperplanes in P1 don't intersect anymore. There's no space for it. And then you can express the Chern class in, because of this fact, there will be never higher powers of H. Then you can basically express the Chern class in terms of elementary polynomial SK in this form. And you find a certain normalization factor, which I call NWL. And then similar, as you have the adjunction formula, but you want the Fano variety, you leave away this 2 and do the same thing. And then you get the Chern classes of the Fano variety, and they are written there. They are also given in terms of symmetric polynomials. And then you noticed, I mean, with a little calculation, that if you evaluate the Chern class, the highest, you have of course to take the highest combination of Chern classes, which gives the dimension of this space, then it's given by these normalizations that I given before. I mean, they are different for the Fano and the Calabi-Yau. That's why I've just put here an X. And so you can calculate these Chern classes. And then, of course, you have also very simple coefficients of the intersection rings. I mentioned before, they match with the criterion of Oguisu to have a fibration. They are also just linear in the hyperplane classes. And that is true for the Fano variety as well as for the Calabi-Yau, only that here this is of course one class more, and here is a 2. And now you get simply the theorem by evaluating nu t and the Feynman graph in finite power series of t. So you take this expression here, for instance, and there is a t, and this t evaluates, and when you bring down the w, you can integrate it, and if you expand this in symmetric powers of the Chern classes, this expression, you get, for each t power, you get a coefficient, and this coefficient is the coefficient I showed you in this table, and the coefficient is the one that makes this formula exactly the generating function of all the connection matrices that you get. So in this way, you know now that you can actually calculate this connection matrix exactly. So it's not a numerical value, it's a certain combination of Zeta values. So this was the proof of these two theorems, which basically give you all the connection. I mean, you know the Feynman graph, let's say in the up to this radius of conversion, and beyond that, this is the complete answer for all L. And so to say, let me come now to the conclusions. So the solution of this Goldilocks amplitude, I would say, is not very hard, as it's an amplitude which is much too easy, but it has probably and hopefully revealed some general feature that could pave the way for further progress in higher loop calculation in more complicated situations. So let me say some of the features that I see as being relevant. So one thing, what you should sort of say, taking more into account is this point of maximal unipotent monodromy. That's actually predicted by mirror symmetry for all Calabi-Yau motifs. And that fits perfectly with the high energy degeneration of the Feynman amplitudes. So if you study the high energy degeneration of the Feynman amplitudes with the gamma class formalism, you get the topological information about the Calabi-Yau, because all the intersection numbers can be actually recovered from that. And then, for instance, for the threefolds, we have nice classification theorems, for instance, by CTC Wall, who says, if I know the intersection ring, if I know the evaluation of the Chern classes, the Hodge numbers, then I know what is the topological type of this Calabi-Yau. So this is basically the Feynman graph will sort of, you get him when you put them in this degeneration, it will tell you what topological type of Calabi-Yau you need. And also this, what is nice about this gamma formalism is that it explains some of this transcendentality structure, because after all, you're just expanding a gamma function, and that's why you get all this Zeta structure. And maybe if you sort of do the master integrals, you can also get higher multiple Zeta functions, but for this integral, you never get higher multiple Zeta functions, because it's just that you expand gamma functions. What we also see is, and that was also a little bit in this work of Kilian, he already know that what are the full period matrix. So we see that these banana amplitudes are also Goldilocks case for starting master integrals. And again, I think this degeneration will tell us a lot about them. And then another thing which I sort of realized by doing this with the student is that this rich databases of Calabi-Yau manifolds and motifs, for instance, provided by people by Kreutzer and Skarke, they have done a list of all the reflexive polyhedra in up to 4 dimensions. Then Almquist, Enkford, and van Straten, that's why this Calabi-Yau operator for L = 4 was, for instance, the ASZE operator 34, because they have a list of those, and you can find them there. That is is at this page in Mainz. And then there is also a very important list about finding these holomorphic solutions for the Fano varieties that we also used. They can be found at this web page of codes called Fano Search. I mean, I wish this thing had a little bit more inverse searching, but they are with a couple of more features, they can become like the integrable tables of the future, at least as the one that extend elliptic integrals to Calabi-Yau integrals. And they can be extremely useful. And then if you combine this with the Skelpanov-Sedovitsky system, you basically can provide super fast and super precise numerical evaluation. So for instance, if you don't know all these Zeta values, then of course you are basically in the woods. You need a lot of time to see what combination of Zeta values there are. But if you know the Zeta values, you can easily check up to 1,000 digits that this is the right amplitude which matches, for instance, in a certain region, the Bessel function, or let's say at this region of attractor point, this periods and quasi-periods. And finally, on a more speculative basis, of course, I'm coming from topological string theory. We actually are not happy with just doing the genus 0 chromophyton invariants, which correspond to the periods, but we want to do higher loop amplitudes in the sense of worldsheet. So we have, I mean, it is true by the gist of mirror symmetry that these periods encode the rational curves on this Calabi-Yaus. But there is a very similar epsilon expansion, and this epsilon expansion, there is a refined version, and in particular in the Nekrasov-Saakashvili limit, there is something which is called exactly the epsilon. And I suspect that these higher terms are related by, like in these quantum periods, by differential recursion relations to each other. And this is, so to say, what exactly happens in the Nekrasov-Saakashvili limit, and which is an integrable system, and that probably could provide a deeper link of this expansion to integrable system. So I think that's all for now.
Thank you. And let's again take a couple of seconds to unmute ourselves. And I see David has a question.
Yes, thank you for this delightful overview. I agree entirely. We as high energy physicists can calculate the high energy, the massless limit, with great ease. We know we will only see from Banana diagram gamma functions on their products, and we can generate for you with great ease that matrix that you showed. I want to emphasize.
Can you sort of prove it in a sense that?
Yes, because the massless diagram is just given in-dimensional regularization by beta functions. And their expansions in epsilon essentially count logarithms, and the logarithms correspond to successive cuts of the diagram. So that was a back of the envelope calculation for me to find the linear combination of my amplitudes that corresponded to Philip and Zenia's Calabi-Yau solutions.
This general solution with the gamma classes, you also would know that, or I mean, it could be. I mean, this general generating function that that you get here. I always work case by case, I'm afraid, right? All I can say. But I mean, so to say, the beauty of having this series of all Calabi-Yaus is you can make really, and that's why I call it analytic structure of the banana graphs. You can basically make proofs for everything, and you don't have to calculate anymore.
Well, when you say you don't have to calculate, I mean, we're interested in numbers, right?
Well, at the end, you expand this thing and you get this expression. So you can do this for all loops. And also it's nice that you can do it, of course, for the massless case. It's just this. For the massive case.
But I have a very important question, an absolutely burning question that comes from your talk.
Yes.
It concerns the difference between the modular behavior where the Hasse-Weil zeta function splits at the singular point,
right,
x equals 1, and this wonderful splitting which Philip and Zenia and Duco and Elmi found at a regular point. Now, the crucial thing from my talk is that the Feynman diagram itself, when you don't cut any of the lines, is not a Calabi-Yau period. The Calabi-Yau period.
I understand that. So
whereas at the singular point, and the magnetic moment of the electron, it is. So the actual thing that we calculate for the magnetic moment of the electron is the diagram cutting no things, and that is the period of the given by a period of the weight for level 6 modular form.
You mean at this point s equal 1, or?
Yes.
Yes.
The diagram itself.
No, I know. This is
Whereas everything in my talk, right, at the other modular points at level 14 and level 34, those were just the solutions to the Feynman solutions, combinations of the Calabi-Yau solutions. So my big question to you is, what is the thing which is not the Calabi-Yau period, the actual value of that diagram itself?
Well, I thought you had found it, but maybe I'm wrong, because didn't you found, so to say, I mean, I thought you claimed you found actually at this point the Feynman graph value, or not?
Yeah. No, it's the difference between when you cut one line, when you put one of the lines on its mass shell, then you get a solution to the inhomogeneous equation. That inhomogeneous term, 120, factorial 5 on my slide, which was on yours, right, refers to the actual diagram before you take any cuts of it.
Sure.
And everything that Philip and Xenia did, right, was for the solutions to the homogeneous equation. So
no, I agree completely. But let me tell you one thing. I mean, it's not true that this will be, that you get exact values only if the Hasse-Weil Zeta function factorized. So basically, the Weil conjecture would say that for general point, I mean, for general rational points, or maybe rational points with extension, you find Hecke eigenforms of paramodular forms, Siegel paramodular forms. So this is just a tiny example that you get, so to say, by luck, that the Hasse-Weil Zeta function calculates and you factorize, and you can do the calculation. But in general, the Weil conjecture tell you there is a Siegel modular form that gives you these values, exact values at all, at rational points. All right.
Yeah, but come to these very specific cases, I would like to know, I really would like to know, because I can give you 10,000 digits of it, what in a mathematical context the solution to the inhomogeneous equation is at the modular points with level 14 and 34.
Right. Let me say, I mean, this is I mean, first of all, of course, this thing is not proven, right? I mean, basically, that Kilian was doing also, and he found actually many more rank 2 attractor points in other Calabi-Yau manifolds. So you can check with high precision that they are equal, but it's not a proof. And what you have to do the proof maybe provides the answer to your question. So what you have to do the proof is you have to construct the Cougar-Zato variety of this special fiber. And this Cougar-Zato variety might give you the answer what this additional period does. But let me ask you, because I had no time for your talk yesterday, and I also have to go to a thesis defense after my talk. But maybe we can talk later.
Yes.
I mean, that would be great.
We talk later. Thank you.
So is it true that you can determine the Feynman graph exactly or not?
The periods and the quasi-periods of the weight 2 and weight 4 modular forms, which are on my slides, which are already on this down there, relate to the Feynman diagram in which I put one of the internal propagators on it.
That is actually more or less.
And then I get the solutions to the homogeneous equation without the factorial 5 down there. And I'm asking you, what is the real Feynman diagram at this modular point?
Yeah, we looked.
Point, it is the period of the modular form, but it's not. Anyway, we should continue.
We looked at that and we didn't find it. So I thought you found it, but now as you're saying you don't.
No. I'll send you a more detailed version of my of my findings. But
okay, very good.
We're taking up too much time.
Yeah, thank you.
Matthias, you're muted.
Thank you. So are there any further questions? I do have a question myself. So if I understand it correctly, one crucial point to go from your first paper to your second paper was that you found this realization where you had a much smaller moduli space. So is this just some coincidence that it is possible in this case, or is that something completely algorithmic that you can also do in any other case?
It's a contrary of algorithmic. So basically, we talked with Matt Kerr, and Matt Kerr looked at this database here. And that's why I think these databases are very important. And he made the observation that, that the holomorphic period is just for, I mean, if you click at this database, you find, you can put in the coefficients of the holomorphic solution, or maybe you can put in the form of the holomorphic solution, then you find this other motive. And then, of course, it is just like a charm. Then everything can be expressed in terms of this simpler motive, and all this these general formulas that I can give for the coefficients, for the transition coefficients, they are just coming like nothing. I mean, just because the cohomology of this other example is so much simpler than the original one. So that's why I'm stressing these databases. I mean, you have to, I mean, okay, I mean, maybe I'm stupid. I could have gotten to the solution, but if you have, let's say, I mean, one of the lessons that I have to say is important. If you have one holomorphic solutions, start thinking in which motives this holomorphic solution does appear. And then you find probably better motives, and that will lead you to more. And the other lecture is, the other lesson that I sort of was getting is that look at the maximal degeneration. It will tell you the topology of the geometry. I mean, that was also what David was saying. I mean, this is very simple. You know that that there is a very physical degeneration, and it's simple, relatively simple to handle. Take this one, engineer backwards over the gamma class. What is the geometry, and you get the rest.
Thank you. Okay, if there's no further questions, thanks again. And yeah, we'll reconvene in a bit more than 20 minutes for the next and last session of talks. And feel free to stick around or take a coffee and chat, and also now use the chance if you have any further burning questions for either Albrecht or for Martijn.
Okay, I believe it is time to get started with the last part of the conference, Elliptics and Beyond. We will have two talks, and the first talk is by Lara Anderson, who will speak or present an overview of Calabi-Yau elliptic fibrations. Could you, yes, please share your screen? Thank you.
So let me begin by thanking the organizers. This has been a fun week for me to participate in virtually. I don't work in Amplitudes at all. My specialty is string compactification. So this has been a fun overview of the sort of the state of the field, and a lot of interesting open questions for me. So thank you for giving me the opportunity to see a glimpse of this. As was mentioned, I was asked when I was asked to speak here to provide a pretty broad overview talk about Calabi-Yau geometry. And the target audience of this talk is non-experts in mathematics or the geometry of Calabi-Yau manifolds. So this will be at quite a broad level, I hope. And I apologize to the experts in the room. Some people know this very well, so this may be a bit boring. For most of the talk, I'll be talking sort of about general review material, and then I'll mention a little bit towards the end about some work that I have done with collaborators. James Gray, also here at Virginia Tech, and our then postdocs, Jin Gao and Sungju Lee, on characterizing elliptic fibrations in Calabi-Yau manifolds, and also some current work in progress with James and with Waddy Taylor at MIT. So that's the plan. Let's see how this works. Let's see, there we go. So the motivation for considering Calabi-Yau geometry that I want to give you a very broad brushstrokes on to begin with is within string theory. Of course, string theory comes with a lot more baggage than just quantum field theory. It's a powerful extension of quantum field theory, But the sort of higher dimensional nature of the effective field theories that we are naturally led to in, for example, 10 and 11 dimensions in string theory means that we are forced, in order to do physics in, quote, the real world, to the subject of string compactifications. So we have to consider solutions of higher dimensional string theories in which part of those directions of space take the form of compact manifold. The process of string theory involves not just writing down a field theory, but a path from higher dimensional geometry through to 4D physics. So the catch here is that we need a robust toolkit in order to be able to extract low energy physics from a string compactification. So in particular, in field theory, we can write down a field theory of any type we like. For example, the standard model, and we're free to choose the mass of the electron to be whatever we'd like it to be in that field theory. Within string theory, many details of this field theory, the form of couplings, the form of potentials, the form of masses, all of these are constrained by the higher dimensional solution, the fact that you have this compact manifold as part of the solution of the theory. And these aren't free knobs you can turn in terms of couplings and masses. They are actually dictated to you by the form of that compact background. So in string theory, we're frequently replacing the question of which effective field theories are we allowed to write down with which geometries are arising in these solution sets. So something that a lot of people in string theory are very interested in at the moment is a Venn diagram of the form of the one that I have here on my slide, one in which you are interested in where within the space of, for example, 4-dimensional field theories, where do string compactifications live? Do they sweep out all of this space, or are they only some of them that can be? So can only some 4D field theories, gauge theories, be extended to also include gravity, quantum gravity in a string context? And also, of course, we're interested in very particular field theories like the standard model and whether we can achieve those in a string context as well. So there's been a ton of work in string theory in this so-called swampland program at the moment, which is trying to answer questions of this type. What types of field theories are allowed? Which ones can be consistently completed in field theory, in string theory, which field theories can be completed? And can we extract patterns, constraints, predictions from these types of backgrounds in a useful way? So this is a very broad brushstrokes motivation for why background geometry in string solutions play such an essential role. Now, in today's talk, I'm going to focus on one particular type of background. This is by no means the only type of geometric solution that appears in string compactifications, but it is one that appears very broadly. And these are Calabi-Yau manifolds as solutions for the compact directions of string theory. So these frequently arise from supersymmetry conditions in 10D string theories. The condition that the internal directions of your space, the ones that you are going to choose to be compact, must be Ricci flat. So the definition that we're going to be interested in is that a Calabi-Yau manifold is a compact, complex manifold which admits a Ricci flat metric. I'm writing this here as GAB bar in terms of the complex coordinates on this internal space. So for example, if I began in 10 dimensions and I'm interested in getting a 4-dimensional theory, then I would have to have 6 compact dimensions, and that's a complex threefold. Now, Yau's proof of Calabi's conjecture showed that such a metric exists if you have a manifold that is so-called Kähler and satisfies a topological condition that its first Chern class vanishes. This is simply the trace of the curvature. This is also one-to-one with being SU3 holonomy as a manifold. Now, Yau won a Fields Medal for completing this proof and proving that for a class of manifolds of this type, a Ricci flat metric must exist. He did not explicitly write down said Ricci flat metric, and this leads to all sorts of problems within string theory in that we would really love to have that metric in order to be able to compute things that we actually want in the field theory, but this is non-constructive. So recent numeric work has worked on trying to generate explicit Calabi-Yau metrics, but in principle, they're still broadly unknown. This, as I just outlined it, was Calabi-Yaus as they arise in string theory. But of course, as we have seen in this workshop, there are many more arenas where this type of geometry is appearing naturally in field theory contexts. So in the context of Feynman graphs and scattering amplitudes, we've heard many examples this week where Calabi-Yau backgrounds have appeared. There's other known examples in the literature in which the vacuum space of field theories, for example, work by Yang-Hui He and James Gray and collaborators showed that the vacuum space of supersymmetric QCD must in fact be a Calabi-Yau manifold. So there are many examples where this type of geometry appears, and there are probably pretty broad energy minimization reasons for that to do with this Ricci flat solution. So this happens in a lot of places. So what can we say about these manifolds? So the first thing we want to try and enumerate is what types of Calabi-Yaus exist. And again, this has been alluded to in many aspects of this week, so I imagine most people have at least heard these results, but let me try and say a little bit about it. You can step up the dimension of the complex n-fold. So for a Calabi-Yau one-fold, this is unique, and this is a T2. This will also be referred to throughout my talk as a genus 1 or an elliptic curve. Just to be precise about it, an elliptic curve is simply a complex description of a T2. So T2 is a real manifold, elliptic curve is a complex manifold, and it's a genus 1 curve that admits a marked point. So it is a genus 1 curve with a slightly enhanced bit of structure. For two complex dimensions, again, if you exclude the product solution T2 times T2, you have a unique solution, the K3 surface, which has appeared in many talks, Matthias's and in Chuck's talks yesterday, for example. K3 surfaces are Calabi-Yau two-folds, real four-folds, etc. There's only one of those. So far, 1, 2 unique solutions, it's looking good, but at complex 3, things break down. There are over 1 billion topological types known so far, and still counting. We do not yet have a proof that there is a finite number of Calabi-Yau three-folds. And although systematic attempts have been made for building Calabi-Yau four-fold data sets, once you get to say 5 and higher, you can actually show that even the standard ways that we have of building Calabi-Yaus, you're going to rapidly exceed computational power, existing computational power in trying to classify these. So for n bigger than 3, you are going to have very large data sets of manifolds indeed. So the simplicity, unfortunately, goes out the window. Okay. So let's say a little bit about three-folds to begin with. These are certainly, from the point of view of the topics this week, this is not the only geometries you'd be interested in. You might be interested in elliptic curves or two-folds or higher dimensional Calabi-Yaus as well. But this is sort of the first example where we have structure that begins to be characterizable and diverse. So let's try and begin there. So as has been alluded to in other talks, a Calabi-Yau threefold has two important structures that characterize its topological type. These are the complex structure deformations of a metric. This is varying what you mean by complex coordinates on the manifold, and these lead to explicit deformations of the Ricci flat metric. It also admits a Kähler structure, and a Hermitian metric on a complex manifold is called Kähler if it can be written in complex coordinates in this form, i.e. only the 1, 1 part is non-vanishing. More specifically, it can be written as dd bar of some complex function. These degrees of freedom in a string compactification would appear as 4D massless moduli of the theory. Wiggles of the metric would appear as 4D massless scalars. And the number of those would be counted by the Hodge numbers of the manifold. Again, this has been mentioned in a variety of talks. For our purposes today, this is only really important in that it allows us to characterize one Calabi-Yau by talking about these topological invariants. The H11 and H21 moduli characterizing the size and shape moduli of the geometry. Okay, so there is a few broad brushstrokes of Calabi-Yau threefolds. Now we want to get to the point that I think most people here would be most interested in, which is you find a Calabi-Yau arising in your calculation in some explicit way. You want to be able to describe it and understand how to calculate quantities of interest to you. So Yau's theorem is powerful, but how does one explicitly construct Calabi-Yaus, and how does one describe their essential properties, calculate stuff? So to begin with, we know that we want compact complex manifolds. So one naturally thinks complex manifolds, let's start with Cn, but of course that's not compact. So it is natural to consider the most simple compactification of Cn into complex projective space, which is to identify a set of n coordinates. Here I wrote z0 to zn up to some overall scale. So any 2 points in this n-dimensional space are identified as the same point if up to a scale they are the same. So an example, of course, P1, which has appeared in many talks, including Albrecht's just now. This is the real manifold of S2. So you can see the compact nature of that in that description. Complex projective space is sometimes written CPN. I'm going to drop the C and just write it as PN for the purposes of this talk. Complex is implied. This thing is Kähler But not, of course, Ricci flat. It has positive curvature. So what can one do with that? You can, of course, define the zero locus of a polynomial. You can consider an algebraic subvariety, P of Zi equals 0. And the notation for this, which again you've seen in a variety of talks, is to write the Pn that you're treating as an ambient space, and in brackets, an integer m, where m is the degree of the hypersurface that you're going to be defining. Now, where does this, how does this lead to a Calabi-Yau? How does this give you what you want? Well, you can just do a very basic problem in GR, which is you can say that this positive curvature ambient space has a natural Kähler metric, which looks like dd bar of a log of the squares, the norms of the complex coordinates. This is called the Fabini-Studi metric. And you can just ask, as a metric subvariety, if I just restrict to this hypersurface, what happens to this metric? So you can restrict to the p equals 0 locus. And it is a pretty straightforward GR calculation to show that the Ricci tensor, Ricci scalar restricted, goes as, Ricci tensor restricted, goes as the following. You get things that look like an integer prefactor, which depends on which projective space you started with and which degree equation you put in it, times the Fabini-Studi metric itself, plus things that are total derivative terms. Now, why is this interesting? Well, if you look at that prefactor, what you can show is that if you take the trace of this, of course, this thing, if this prefactor vanishes, then all these higher derivative terms under a trace vanish, and you will end up with the trace of the Ricci tensor being 0, i.e. C1 being 0, if you have a numeric correspondence for an m-dimensional hypersurface in a n-dimensional projective space, then you will end up with a Kähler manifold with C1 equals 0, and so by Yau's theorem, this will be a Calabi-Yau manifold. Again, just dimension counting, if we have a n-dimensional projective space, we will have a Calabi-Yau n-1 fold because we cut it with one equation. So the classic example, which you've seen in a variety of talks, is of course the quintic polynomial in P4. 0 locus of a degree 5 equation homogeneous, say of this type, gives you a Calabi-Yau threefold. Now, this idea of how to build Calabi-Yaus is useful for a variety of reasons. What we're really interested in is Ricci flat solutions to, say, string backgrounds or whatever field theories we're interested in. Those need not be algebraic. We might be solving problems in differential geometry, but by writing algebraic equations of this type and using Yau's theorem, we've substituted problems in differential geometry for problems in algebraic geometry, which in general are much easier. Not all, but in this case, many of these problems are. So what we can now ask is, can I build, how many Calabi-Yaus could I build using a technique like I just described? So consider a projective space, write an equation in it. It's easy to show that this condition to have the first term class being 0 can be naturally extended to multiple hypersurfaces intersecting. And you, again, have seen in Matthias's talk, for example, examples of this type. So you can show that the Calabi-Yau condition for multiple hypersurfaces is that the degree, the sum of the degrees of those hypersurfaces has to add up to the dimension of the projective space. Dimension of the projective space plus 1. So in this case, I'm deriving here a P5, the two elements of this bracket separated by a comma. These are saying that I write down two equations that have to be satisfied, both of degree 3. The sum of those degrees is 6, which is n plus 1 here. So this condition is satisfied. And again, this is going to be a C1 equals 0 Calabi-Yau manifold. You can step up how many equations you want to write down in bigger and bigger ambient spaces. And you can ask how many manifolds could you build? So for example, we could build a 3-3 hypersurface in P5, 4-2 hypersurface in P5. This is satisfying the numeric condition we need. 2-2-3 in P6, so on. You might ask, can I just keep going forever? Can I make bigger and bigger projective spaces, more and more equations, cutting out and continue building manifolds? You actually, for single projective spaces, you stop at the 5 that I have listed here. So the quintic and these 4 additions. The reason for that is that pretty soon, as you do the combinatorics problem of trying to write down in some Pn a set of equations that are going to give you, say, a Calabi-Yau threefold, what you find is that you have to include linear constraints in order to have the sum of degrees work out right. And in fact, a linear constraint in a Pn is just a Pn minus 1. That's easy to see in that you can just solve the linear for one of the coordinates and end up with a bunch of other coordinates with exactly the same scales scaling properties that you had before. So there are only these 5, they're called cyclic Calabi-Yau manifolds that can be defined in a single projective space, Calabi-Yau 3-folds, I should say. Of course, 2-folds and 1-folds you can do very similarly. There's a few descriptions of those, but because we know there's only the elliptic curve and the K3 surface, these are just different descriptions of the same manifold. Okay. What generalizations might one consider still further if one wants to build more manifolds? You can change the notion of scaling that you're introducing to your complex coordinates in order to make them compact. So I chose to compactify my coordinates by identifying points such that the entire vector was identified up to a scale. But you could actually scale each coordinate separately, and that's what's described here. This is a so-called weighted projective space instead of projective space. So here, each coordinate is scaling with a different power of this parameter lambda, and we write that as a p where the subscript here denotes the weight of the coordinates. So this is 1, 2, 3 because it's telling me the power of lambda that each coordinate lives in. Again, there is a simple condition on such a space for the degree adding up to the sum of the weights of these coordinates. So in this case, a T2 Calabi-Yau 1-fold could be written as a P1, 2, 3, which is a complex surface, and a degree 6 hypersurface in that. You can also generalize the description so that you have product ambient spaces. Again, you saw this, for example, in Albrecht's talk this morning. You can have, instead of having a single projective space, you can define your ambient space to be, say, a product of P1 and P2, and then write a single equation, that's what this column represents, as, for example, a degree 2, 4 hypersurface, where 2 is telling you the multi-degree in these coordinates, 4 in these coordinates. This has to be homogeneous 2, 4 polynomial in such a space. Here, this product naturally can, you can extend as high as you like, and for each row in this case, you have to still satisfy this Calabi-Yau condition that the degree is 1 more than the dimension of the projective space. Sorry, that should be a P3 there in order to satisfy this, P1, P3. Okay, so if you ask how many manifolds now can I build of that type, if I extend to products of projective spaces, this was actually first classified in the 1980s by Philip Candelas and collaborators at CERN. And they found that there were 7,890 Calabi-Yau 3-folds that could be built in generalizations of this idea. This was a remarkable feat of 1980s computing. This was done on magnetic tape at CERN. And if you actually try and run a classification of this type, so say I want to build, I'm going to extend products of projective spaces according to this rule that the equations have to add up so their degree is 1 more than the dimension of the projective space. If you set that algorithm up in a stupid way, even on a modern computer, it would never finish. So the fact that they tuned this in such an intelligent manner to actually finish this in the 1980s was pretty impressive. And this constituted the first large data set of Calabi-Yau 3-folds that had been built. So these 7,890 manifolds. You can also still further generalize this, and Albrecht described a bit of this in his talk, to more general toric varieties, changing the scaling relation, not necessarily having products, but multiple directions with different scales. These lead to also a simple way to build Calabi-Yaus as hypersurfaces or as complete intersections. And using that toric generalization of these ambient spaces, so far more than 1 billion Calabi-Yau 3-folds have been built. This is the so-called Kreutzer-Skarka database, also mentioned in Albrecht's talk. Okay, so hopefully this gives you a little bit of a feel for, we went from an abstract condition for Ricci flat metrics to now we have explicit algebraic constructions in projective spaces or generalizations thereof. What else do we want to probe? So let me try and say for the Calabi-Yau 3-folds a little bit about what this data set of 1 billion manifolds lets you extract. So I apologize, on this slide, my axes got cut off. This picture is a famous plot of the Hodge numbers of the Kreutzer-Skarka dataset. And the axes here, the horizontal axis is the difference in the 2 Hodge numbers that characterize a 3-fold. This is H11 minus H21, and the vertical axis is the sum, H11 plus H21. Now each dot here represents a topologically distinct manifold, a different value for the Hodge number pair H11, H21. So you have a whole bunch of dots and 500 million manifolds as written here. Now we have to say, what do we want to extract from this? So let's try and make some observations about what we might say. So the first thing that you would observe about this diagram is Calabi-Yau mirror symmetry. So let me go back. you look at the fact that everything that appears for one value of h11 minus h21, there's a value on the other side of that axis. So positive and negative x here, these appear in pairs. So this is mirror symmetric across the vertical axis. This was first observed by physicists, including by Candelas and collaborators, and also independently work in the gauge linear sigma model community. And at first, mathematicians didn't buy that this was actually going to be a general feature of Calabi-Yau's, that for each value of Hodge numbers, h11, h21, there should exist another Calabi-Yau with those integers interchanged. Of course, it was proven to be the case, and again, extended into homological mirror symmetry, Netherfield's medal, good stuff happening there. So mirror symmetry, powerful feature of Calabi-Yau's. The other things you might want to know looking at this data set is there a finite range in topological type appearing for Calabi-Yau threefolds, at least for these types of manifolds that we've built so far? For these data sets, of course, there is. For more general Calabi-Yau's, it's still unknown for threefolds, whether there's a finite range of topology. In the manifolds that have been constructed to date, the smallest Hodge numbers appearing are 1 and 1, the largest 11 and 491. In 20 years of studying Calabi-Yau's, of trying to extract their properties, this data set has been getting denser and denser, but not bigger, which is to say that the boundaries of this plot have remained intact in 20 years. The shape of the plot has a lot of structure, and we're going to return to why that is later in the talk. So specifically, if you go back here, the fact that there are these interesting, parabolic structures here that sort of get mirrored as you go further down. There's a lot of structure as to which topologies are actually appearing for threefolds, and you could ask, why is that happening? And as has also been discussed in, for example, Chuck's talk yesterday, it is possible to actually connect different dots in this diagram through so-called geometric transitions. So these are simple operations where the manifold becomes singular, and you can repair those singularities through simple surgery, for example, replacing a singular point by a two-sphere. There is, for all the known data sets, for example, the initial 7,890 CC threefolds, all of them can be connected to each other using simple geometric operations of this type, which are known in string theory to actually be legitimate directions in field theory. So you can actually extend the field theory through these types of transitions. A conjecture, actually even weaker than a conjecture, a so-called fantasy by the mathematician Miles Reed, is that all Calabi-Yau threefolds should be connected by these types of geometric transitions. So those are some initial observations we might make about the data set as we understand it so far. So in the following slides, I'm going to be taking a little bit of a deeper dive to trying to illustrate why this data set, at least for threefolds, might be finite, and how to characterize some properties of its structure. Now remember, for all of us, if you're not a mathematician, right? You want to say, as a physicist, I am seeing these Calabi-Yau geometries appearing in my calculation. I would really like to be able to constrain that set and say, this is the range of things that I can get, so that I could constrain something about the field theory that is underlying my real problem in a meaningful way. So I want to be able to extract physics information from a knowledge of what's going on with Calabi-Yau's. But if I say I'm going to work towards trying to characterize or prove to be finite a set of Calabi-Yau's, you might ask, is that actually a question? Is that a task for a physicist to be doing? Shouldn't mathematicians do that? And the answer is it's partially yes. But I don't have space to illustrate today, but there's actually a remarkable interplay, at least in string theory, between the consistency of field theories that arise in string compactifications and this underlying geometry. So examples, for example, the range of Hodge numbers of Calabi-Yau threefolds. This has been strongly linked, for example, in 6-dimensional compactifications of F-theory. You can prove that through anomaly cancellation conditions that you would have anomaly inconsistent field theories if you had Hodge numbers larger than the ones that have already appeared in this Kreutzer-Skarka dataset. So this 11,491 is actually a firm bound in terms of anomaly consistent 6D string compactifications. Likewise, this was work done by Waddy Taylor. I should have put refs on this slide and didn't. Consistency of 2D sigma models. Oguri and collaborators have looked at consistency bounds on possible H11 for all threefolds. Just to give another example, chiral indices and heterotic theories are related to Donaldson-Thomas invariants of Calabi-Yau's. So there's a bunch of structure there that can be explored in terms of consistency of field theory and consistency of Calabi-Yau background geometry. So there actually is potentially more information at the intersection of the math and physics of this than there would be just mathematically or physically alone. Okay. So let me give some practical tools that some of these you have seen before. Part of this was alluded to in Albrecht's talk. Let's ask the question, how do we determine if two Calabi-Yau threefolds are the same? We could ask this about fourfolds and higher as well, but let me start with threefolds. There's a very useful theorem by Wall from the 1960s, which shows that there is a vector of data that you can compile about this Calabi-Yau, namely its Hodge numbers, which we've already discussed, the triple intersection numbers of divisors within the manifold. A divisor is simply an algebraic hypersurface within the Calabi-Yau itself. So here you have a basis where ABC runs over however many independent divisors you could write down, and the second Chern class of the manifold. If you compute, all of these are integer quantities, so you compute this set of integers, and if it is different for two Calabi-Yaus, then he showed that these are not diffeomorphic as manifolds. The converse of this is also interesting. So if you say I compile that list of integers, it is the same, then that what Wall's theorem shows is that these manifolds could be the same as real manifolds, but not necessarily diffeomorphic as complex. So for our purposes, when I say there's roughly 1 billion Calabi-Yau threefolds known, what do I mean by that? There's only 500 million hypersurfaces in the Kreutzig-Skarka dataset, but by analyzing intersection numbers and other things that appear, you can estimate that there's at least 500 million, probably much, much more, distinct manifolds existing in that set by Wall's theorem. Another thing that's going to be important for the rest of my talk is that Calabi-Yaus also can exhibit substructure. And again, you've heard about this from a variety of talks this week, specifically the existence of fibrations. So the fibration is a surjective mapping from your Calabi-Yau manifold X, say, to some other complex manifold B. And the existence of such a fibration is deformation invariant, i.e. topological, for Calabi-Yau n-folds where n is greater than or equal to 3. So if you can see something about the substructure of the manifold, that also can characterize which Calabi-Yaus are available to you. And as we'll see, this breakdown of the manifold into fibration can actually give you a big handle on integrals over the Calabi-Yau, properties of its topological structure. A lot of interesting features, even the shape of its metric can be affected by the existence of this substructure. Also, a very key result, if a manifold is fibered, the number of T2 fibered Calabi-Yau threefolds is finite. So there's one data set of Calabi-Yaus that is proven to be finite, and I'm going to come back to that in an important way in just a moment. Okay. So let me just say, again, most people probably know this, but let me, for those of you that don't work with this kind of geometry, let me try and define things. So what does it mean to be fibered? What do I mean by substructure? So the simple idea here is to try and morally stack one simple geometry over every point of another. So the formal definition is a fibration is a continuous mapping, pi from X to B, such that for almost all points in the base, BB prime, the preimage of the projection map, i.e. the fiber, is homotopic, i.e. smoothly deformable. This property is called the homotopy lifting property. The fiber we define to be the inverse image of a point in the base. The base is some complex manifold. So examples for non-mathematically inclined folks, R2, for example, is a fiber of R over R. So at each point in a real line, you have a copy of another real line over every point. Likewise, the cylinder is a fibration of an interval over S1. So you have a circle, over each point in that circle, you fiber an interval. The Mobius strip is interesting because unlike my first two examples, this is a non-trivial fibration. Trivial in the sense that if I had a direct product of R cross R or a direct product of S1 across this interval, these would form these simple manifolds. But the Mobius strip is a fibration, again, of an interval over S1, but it has a non-trivial topology to it. It has a non-trivial twist as you move around the circle. Interesting result, Calabi-Yau manifolds must have Calabi-Yau fibers of smaller dimension. So the only fibers that are going to appear, the only fibrations are ones which have Calabi-Yau substructure to them. So for example, Calabi-Yau threefolds can have T2 or K3 fibers over some bases. If it's K3 fibered, then by topology, you can show that the base must be a P1. Okay, you've seen in Chuck's talk, for example, yesterday, the importance of special forms of fibered manifolds. So in particular, I'm going to be talking a little bit about so-called elliptically fibered manifolds. Just to get the terminology straight, I will say elliptically fibered, genus 1 fibered, or T2 fibered. The difference here is that an elliptically fibered manifold has this marked point, and that means there exists a section i.e. a mapping from the base back up to the total manifold. If the manifold admits the section in addition to its projection mapping, then we say it is elliptically fibered. If it doesn't, if it just has the projection, then it's either genus 1 or T2 fibered. But if we have an elliptic fibration, there's a nice normal form that you've already seen in Jacques' talk, which allows you to write a description of a P123 6 elliptic fiber over every point in some complex base manifold B. Here, UI are coordinates that live in the anti-canonical powers of the anti-canonical bundle over that base. These fibers need not be the same absolutely everywhere. So for generic points in the base, they are smooth T2s, but over special points in the base, those T2s can degenerate. These degenerations, again, we've heard in various talks, can have significance both for the physics in string theory as well as for amplitudes and other interesting applications. The reason that I'm primarily going to try and talk about manifolds that admit fibrations for the remainder of this talk is that they provide an important window into considering finiteness. So as I already mentioned, in work in the 1990s, Grassi and Gross showed that there is a finite number of Calabi-Yau threefolds that can be written as a T2 fibered over some complex surface, B. Basically, the proof goes by showing that because you have a mystery Calabi-Yau manifold, you can break it into a fiber and a base, and you can characterize which base surfaces you can have and then how complicated the twist, just like the Mobius strip, how complicated can you twist this T2 over every point in the base. This gives you a very powerful decomposition. Instead of talking about some general, complex threefold or real sixfold, you're able to break it into much simpler substructure. This type of proof has been recently generalized by De Cerbo and Svaldi for bases for Calabi-Yau fourfolds and fivefolds that are elliptically fibered. This is almost a complete proof of finiteness for all elliptic 4 and 5 folds. There's a technical detail missing, but for the most part, it is strongly believed that those are also finite and nearly proven. So another statement about these special normal forms, there's a theorem due to Nakayama that says that if you have a Calabi-Yau threefold, which is elliptically fibered, i.e. genus 1 fibered with section, then it is birational to this special normal form referred to as a Weierstrass model. Again, this is this simple description of a P123 elliptic fiber over each point in the base. Weierstrass models are a central tool in the study of Calabi-Yau fibrations. And again, the sort of the big in for extracting physics is because you can break your manifold into pieces, fiber and base over each point. You can characterize which base geometries can arise. You can characterize how the fibers can degenerate over what codimension in the base, how singular can they get, how, what types of degenerations and completions can you write down? And a lot of work has been used, these sort of simple models, these simple descriptions of elliptic fibrations to try and span a huge description of a huge range of different topological types of Calabi-Yaus and describe what's possible. Waddy Taylor and collaborators in particular have done a ton of work on Weierstrass models within the space of toric Calabi-Yau hypersurfaces. They showed that, for example, this mirror symmetry description that I mentioned that is evident in the Kreutzer-Skarka dataset in elliptically fibered manifolds can be broken down into fiber-wise mirror symmetry. There's also some very nice work by Paul Ullman along similar lines. So there's a bunch of interesting structure you might want to explore using very simple descriptions of fibered Calabi-Yau geometries. But let me take a step back for a second and say again, I'm trying to give you an overview of Calabi-Yaus. I'm talking about Calabi-Yau threefolds because these are, come with many topological flavors. So why am I going to focus on these fibered guys? I want to ask the following question, and this is one that my collaborators and I have thought about recently in some detail, which is, suppose we are given a mystery Calabi-Yau n-fold, and we would like to know, okay, we know that the set of fibered guys is finite, but let's take some general one out of the data set of all Calabi-Yaus. Doesn't need to be finite. Sorry, it doesn't need to be fibered. Can I ask, is it fibered? Is it genus 1 or elliptically fibered? You could also ask K3 fibered. You could ask detailed questions about what types of fibers it has, whether there are sections to those fibrations. And do we have a toolkit for actually deciding within a general set of Calabi-Yaus, where do the fibered ones live? Fibered ones are much simpler to characterize. They can be proven to be finite. You can calculate with them very easily. So where do these fit in this broader data set? So the first thing is that if you take known data sets of Calabi-Yau threefolds, the CC threefolds that were initially built by Candelas, the Kreutzer-Skarka toric hypersurfaces, you can make two immediate observations. The first observation is that almost all, and I mean that very strongly, almost all known Calabi-Yau threefolds and fourfolds are fibered. They admit elliptic K3, Calabi-Yau threefold fibrations if they're fourfolds, and so on. And the second immediate observation is that generic manifolds do not just admit one description as a fibration, they admit many, order tens, hundreds, or thousands of different vibration descriptions for one manifold. So what can we make of this? So let me, with my remaining time, try and give you a bit of a flavor of what that looks like. So here I have plotted the Kreutzer-Skarka data set of Hodge numbers of Calabi-Yau threefolds again. And these blue dots, this I took from a paper from Waddy Taylor from 8 years ago. This is much denser now. These blue dots fill in almost all the known points in Kreutzer-Skarka with elliptically fibered manifolds that also have that topology. So you can show that the topological types are very readily spanned by elliptic fibrations. You can do a bit better in terms of looking at simple data sets like the complete intersections in, say, products of ordinary projective spaces. I'm sorry about that. My desk phone is ringing. So for Calabi-Yau threefolds, for example, 99.3% of all the manifolds in that data set are fibered. And if you look at the data set of Calabi-Yau fourfolds built in products of projective spaces, these were also classified by Gray, Haupt, and Lucas a few years ago. It's even stronger, 99.9% of all those manifolds admit fibrations. So how do you tell that a manifold is fibered or not? So the first pass is, if you look at a manifold, here's a CC configuration matrix. Here is the ambient space. These two columns are telling you about the degrees of two complete intersection hypersurface equations inside this ambient space. And what you can see is that by the degrees, if I were to pick a solution to this first equation in red and then substitute it into the second, what I would get would be a cubic equation in P2. If you remember our single projective space description of Calabi-Yaus, that is n+1 degree inside a Pn. This is a Calabi-Yau onefold. So over every point in the solution of this surface, I will have a T2 in this manifold. So from the algebraic description of this manifold, it is very evident that I have a T2 fibration. This need not be the only type of T2 fibration it emits, but it's pretty obvious to see that this is T2 fibered. Likewise, here's a Calabi-Yau fourfold below. In different colors here, I've highlighted this blue describes the degrees of an elliptic curve inside the first three projective space factors. If I add in the red to the blues, that gives me a K3 fibration to this manifold. And if I add in the green, that adds a Calabi-Yau threefold fibration of this fourfold. So this fourfold is fibered by threefolds, twofolds, and onefolds in a nested fashion. So it has a threefold fiber, which in turn is K3 fibered, which in turn is elliptically fibered. Okay. Point of interest, when you see an obvious fibration of this type from the algebraic description of the manifold, typically there isn't just one, there can in fact be many. So when you write down a CC manifold of this type, remember that the order that is appearing for the ambient space projective space factors and the order that I write the defining equations in, those are totally arbitrary. So I'm free to rearrange rows and columns as I like. So here I can rearrange these two manifolds to actually show that this particular manifold is the same one, just rearranging equations, rows and columns. And I can show that this is fibered over two different bases. Here a red base, this has a T2 fiber over a 1, 1, 1 hypersurface and a product of 3 P1s. This guy is elliptically fibered over P1 times P1. Okay, so the number of fibrations per sort of algebraic type of manifold called a configuration can be plotted for different manifolds. You can see here that the number of fibrations, the sort of multiplicity of what's appearing can be plotted for CC threefolds. You can say how many of them have 5 fibrations, 10 fibrations, and so on, 35 fibrations. This is the fourfolds up here. Some of the fourfolds had 350 obvious inequivalent fibrations from this type of description. Okay, I'm running short on time, so I'm just going to give you a flavor for what one can extend further. What my collaborators and I have worked on is trying to say for a general elliptically fibered manifold, what I want to characterize is not just whether I can spot a fibration from the algebraic description, but whether the manifold is really fibered. So fortunately, there is a powerful mathematical result, which was formulated for threefolds by Wilson and Nogiso, and conjectured to hold more generally for Calabi-Yau n-folds by Kolar, which allows you to characterize whether the Calabi-Yau admits a fibration or not, purely in terms of intersection numbers of the Calabi-Yau, so topological data about intersection of divisors, and some statements about the cone structure of those divisors. So specifically, if X is a Calabi-Yau n-fold, then it will be genus 1 fibered if and only if there exists a 1-1 class D, so divisors are dual to 1-1 forms inside Calabi-Yau n-folds, such that this thing has D dot C greater than 0 for every algebraic curve within the manifold. Its intersection to the dimension of X power is 0, and its dimension to the X minus 1 power is non-zero. So this, not going to be clear to this audience why you would be interested in this, but the point is it's actually a strong way to be able to unpack just from topological properties whether a manifold is fibered or not. So my collaborators and I tried to do this for some data sets of Calabi-Yaus, and what we showed, so I'm gonna skip this slide. Basically, we gave sort of an intuitive description of what this criteria is providing for you. And what we wanted to do was to say, can we actually take a data set of Calabi-Yaus and exhaustively say how many of them are fibered? And again, can we see if this fibration structure is sort of ubiquitous in data sets of Calabi-Yaus? So we began with the oldest data set of Calabi-Yaus, the 7,890 CC3 folds, and we classified all possible fibrations that could arise. There's some technical issues to how you actually accomplish this that were hard to overcome. Not going to talk about them today. But let me try and show you the results. So of that 7,890 CC3 folds, what we found is that there are about 400,000, sorry, missing an O there, 400,000 fibrations for that data set as a whole. For example, there were 377,000 genus 1 fibrations and 200,000 nested K3 and elliptic fibrations that appeared. I can't give you a full number for the number of fibrations that appear in that data set because they can get very big, in fact, infinite for one manifold. So the anti-canonical hypersurface in a product of two Del Pezzo 7 surfaces, that guy gave rise to 15,000 different fibrations. And in fact, one manifold, the so-called Schoen threefold, gives you a parametrically infinite set of distinct elliptic fibrations. This is a self-Beer manifold with Hodge numbers 1919 that it crops up all over the place in string theory. All right. Here is the punchline for physics of what you want to actually extract from this. What we see is that we are able to actually analyze which Calabi-Yaus have fibrations. And we find that for this data set, they are essentially all fibered. And there are hints that in fact, all Calabi-Yaus with T2 fibers can undergo simple geometric transitions to those that do not. So you can connect fibered and non-fibered manifold in very simple geometric transitions. This was proven for H11 equals 2 by Wilson. With Waddy-Taylor, we're trying to extend this further. The scans that we have done so far on both the toric and the CC3 folds lead us to actually conjecture that all Calabi-Yau 3 folds with H11 greater than 19 will be fibered. So again, as people interested in amplitudes, why is this of interest? Because this description might allow you to simply decompose the mystery Calabi-Yau geometry that is determining your amplitude in a very simple way. So there is a possibility that this description may hold for everything and give you a clean handle on what you want to describe. So I will conclude here. Hopefully this broad overview has shown you Calabi-Yaus appear in a wide range of string and field theories. Their properties and finiteness can be an interesting intersection of math and physics. Relatively new work has shown that almost, in fact, essentially all known Calabi-Yau manifolds are elliptically fibered generically with multiple fibrations. And we're developing a toolkit for being able to systematically decompose these things into fiber and base. This might provide a window into finiteness in the future and hopefully a new set of computational tools that might be relevant. So with that, thank you for your patience and thank you again for a great week.
Yes, let's unmute for a moment in order to thank Lara. Yeah, so we are rather short in time, but I see David already raised his hand for what I hope is going to be a short question, please.
Yes, it's a wonderful overview. I'm reminded Ernest Rutherford said there are two types of science, physics and stamp collecting, and mathematicians are very, very good at stamp collecting, you know, in deep mathematical structure. But what happens to us is that we hit Calabi-Yau 3 fills at 4 loops, but then we can go on to higher loops. So we're kind of going on the opposite, on the other axis from what you're doing. So can you look at the 3 folds that we find and the 4 folds that we find and see what it is that physics selects that's mathematically distinctive from this?
So there certainly is a lot of structure that you can extrapolate to Calabi-Yau n-folds. I gave a flavor of 3 folds just to show you of some of the complexity of characterizing these things that arises. But yeah, depending on what you want to know, there's some things that are very easy to extract for Calabi-Yau n-folds in general, some things that are harder. Indeed, for certain families, so for example, the one that has appeared in simple classes is, a single hypersurface and a single projective space that appeared in a number of talks. That's very easy to characterize for any n. You can sort of say every possible property of that guy you want. So for some families, you can do things in arbitrary generality. The question is, can you characterize how many different types might arise for some amplitude? I guess that would be the question. So, if you're sure you're only in a subfamily, then you're good. You could maybe calculate everything you want. If you would like to run that backwards and say, imagine that every, one of these topological types might appear for some amplitude, what could you say that might be harder to characterize for?
Thank you.
Okay, thank you very much. And thank you very much again for this really amazingly clear and beautiful talk. Before we actually switch to Francis Brown's talk, I would like to ask you to unshare your screen such that I can actually share mine. And I'd like to do that by showing an announcement. So we had conferences about elliptic integrals, Feynman integrals, the mathematics behind it, and for the last couple of years. And while this year we have an online meeting, we would like to announce the meeting for next year, which we hope is going to be a real workshop at the Mainz Institute for Theoretical Physics. It's going to be called Elliptic Integrals in Fundamental Physics, and it's going to happen from 14th to 18th of June in 2021 then. Of course, unlike for virtual meetings, the space is limited. Nevertheless, we will make sure to have the talks broadcasted that everybody of you can actually attend this conference, either virtual or in person. So please note the time already. We hope that the conference or the workshop is going to be a real workshop. So the address of the web page is written up here. I'll leave it on for another couple of seconds while announcing the next talk. So our next speaker is going to be Francis Brown. Francis, could you please share your screen?
Thank you very much for the invitation to speak. Claude suggested that I talk about this topic. Before I begin, before I forget, let me just say from the very beginning that an L function is a more general version of a zeta function. So the words zeta and L are sort of mixed up historically, and I will flip between the two. Okay, so let me begin with a bit of provocation, and I'd like to raise a completely crazy question, which is there a formula for period integrals such as the ones we've seen in this conference? So here, omega is an algebraic differential form on an algebraic variety defined over the rationals, let's say. And sigma is a chain of integration whose boundary is contained in some algebraic subvariety. So this doesn't seem to make much sense, but it's a theme that recurs in this area, in amplitudes generally, where we have a quantum field theory or a string theory, and we want to be able to predict the types of numbers and functions that are going to occur in it by pure thought. Okay, so what possible sort of answer to this question could make any sense at all? So let me begin with a very classical example. Here's a period integral everything is very algebraic. From 0 to 1 of this 2 form. And it has a formula which is given by the product over all primes of 1 minus 1 over p squared inverse. So that's what I mean by a formula for this integral. And I think we all know how to do this, and that's because the integral I is simply zeta 2, which is an easy exercise and was known by Leibniz in the 17th century. And zeta of 2, or the zeta function, the values of the zeta function are defined to be infinite products over primes. So here's a more non-trivial example. Oops, sorry. So up here we have now a triple integral in 3 variables, x, y, and z, of this rational, this quotient of polynomials. And many of you will immediately be able to recognize the physics lurking behind this. You'll be able to spot some secret semantic polynomials. I think this integral actually may have occurred in one of David's recent talks, perhaps not this one, but a recent one. And you can show that this integral also has a formula. It's 4 times pi square root of 15 times LF of 2. So L here is again an L function. It's defined by an infinite product over all primes of some very simple factor here. Well, this P over 15 here is a Legendre symbol. And AP is an integer, which is very mysteriously related to the number of solutions to this equation, which is the denominator, over finite fields FP. So something very subtle is happening here, is that this product actually only converges when the real part of S is bigger than 2, but we need to evaluate it at S equals 2, which is a priori not a legitimate point. So something very subtle is happening here. And in fact, this example that you may know very well, and we kind of take these things for granted, is actually illustrates some of the deepest and most celebrated results in number theory over the past few centuries even. So it illustrates some of the really big theorems in mathematics. Okay, so this brings us to the subject of L functions. There's a very deep and very conjectural program that goes back all the way to Euler. And the list of names of people who've spent their entire lifetimes working on this would fill an entire slide. So I've been very brief here. And very roughly speaking, is to look at L functions and interpret their values as periods. So occasionally, by accident, periods will happen to be values of L functions, and we've seen many examples of this. However, it will be exceptionally rare for a period integral to happen to be the value of an L function. Clearly, if we take 2 numbers with infinite products and we were say to add them together, that's going to destroy the infinite product structure completely. So that's something we're going to have to give up. And only very special periods have any chance to be L values. So I've put a little footnote here. Those of you who know about motivic periods, you can decompose a motivic period in complete generality into an F alphabet. So many of you are familiar with this in the case of multiple zetas. A necessary condition is that your period should be a single letter in that F alphabet. But that's nowhere near strong enough. You need many more conditions to have any chance of being an L value. Okay, so that's not much help to us. And the question I want to raise then, which is a bit wacky, is whether there could possibly exist mixed L functions whose values actually capture all periods. So I would love it to be the case that any period could be the value of something yet to be defined, which is a mixed L function. Now, the problem with this very heuristic and very speculative picture is that both sides are very mysterious. The left-hand side, well, there is no definition, certainly no agreed definition of what a mixed L function should be, let alone or whether it should exist at all. And the other problem is that, you know, we can write down lots of random periods, but there are very few whose structure and geometry we really understand. So there's not much evidence to go on. And so what I'm going to do in this talk is give a very tentative first definition of what a mixed L function might be. This is by no means the final word on this question. The theory of L functions took 300 years of trial and error to develop. This is just a first step towards this very, very conjectural picture. But in any case, what I will do is define some new objects, and these new objects will in fact be connected to a lot of interesting mathematics, which relates to some of the topics that have been studied in this conference. And that's what I want to explain. Okay, so a quick plan. So the first part is going to be a very rough review of the classical theory of L functions. Many of you know this very well already, so please indulge me. So the setup here is we want to consider not just any old L functions. There are plenty of L functions that don't fit in the context I want to consider. So what we like to consider are what are called motivic L functions. I won't say what that is, but they come from geometry in some sense. There are plenty of L functions that don't come from geometry. But the ones that come from geometry are Dirichlet series, so sum an over n to the s, with the property that they have an Euler product, a factorization over all primes, where each factor is the inverse of essentially a polynomial in p to the minus s. And that polynomial is related to geometry in the sense that it very approximately relates to counting points on algebraic varieties over finite fields. More precisely, it's related to the determinant of the Frobenius on the Elliptic cohomology. But let's not worry about that. So in any case, we have a very large supply of very natural Dirichlet series which come from algebraic varieties. And what you can do is complete it. So the L function on its own doesn't have great properties, but you complete it to a function called lambda. And you do that by multiplying by a certain number of gamma functions here, which are called gamma factors. You might want to multiply by some power of pi, and then some integer to the minus s over 2. So n here is called a conductor, and it contains information about primes of bad reduction. The gamma functions here this factor here is entirely determined by some integers ni, and they can essentially be read off the Hodge theory and the action of complex conjugation on the cohomology of your variety. So Serre gave a very precise recipe for how to construct this completed L function from your motivic L function. So once you've completed your L function, you conjecture that the function lambda has a meromorphic continuation to the whole complex plane. In fact, you conjecture a lot more. You can say something about where you expect the poles to be. It needs also to be bounded in vertical strips. There's a whole bunch of things that are conjectured, which I will gloss over. And then there should be a functional equation. So here I've made an assumption. I've written here self-dual case only. In general, if you do lambda m of, if you look at this equation, what happens is you get different L functions appearing on different sides of the equation. You get what's called the dual motive, but let's not worry about that. For most of the talk, I'm just going to look at this case where you get the same L function on both sides. So here we have lambda of s equals a number which is necessarily plus or minus 1 of lambda of w minus s. And these conjectures are incredibly deep and incredibly difficult, but in all the cases that we're going to look at, very simple and very classical L functions, these will all be theorems. And then the matter in this subject is that the values of L functions at integers are very interesting and encode arithmetic information. So there are basically, so this is the sort of the condensed, very condensed version of the theory. There are essentially two different types of values of the L function. Let me ignore the fact that, of course, these functions can have poles. They can vanish as well. When they vanish, you want to take derivatives, but let's ignore all of that. Roughly speaking, there are two types of values you're interested in: the critical values and the non-critical values. So the critical values are the ones where the integers n, where n is neither a pole of the gamma factors. So recall the gamma factors are here, and we know exactly what the poles of gamma are. So they're not a pole of the gamma factors occurring in here. Neither are they a pole of the gamma factors occurring in this L function on the other side. So that's a critical value. It doesn't mean that the integer is inside the critical strip. Okay, that's an accident of vocabulary that the word critical is used in both contexts. And we'll see an example where critical here does not imply being in the critical strip. So Deligne made a conjecture about critical values. And Beilinson later made a conjecture about non-critical values, which are all the other values. But in both cases, it's expected that the values, the integers of these L functions are periods. Okay. So let's do some examples. So amazingly, in this theory, that if you take the trivial motive, which is just a point, the cohomology of a point, you might expect you just get the function 1 or something, but you don't. You get the Riemann zeta function. So the most trivial possible L function is the Riemann zeta function. And you can think it's the sum of 1 over n to the s, as we all know, and it has a factorization. Of course, only for the real part of S sufficiently large. The completed version was called Xi by Riemann, and it's a power of pi times a gamma factor times zeta of S. And in this case, the functional equation relates S, Xi of S, and Xi of 1 minus S. And in this situation, as we all know, it's very easy to show that the zeta values are periods. They're given by this very explicit integral. And critical in this case, if you sit down and work out what critical means, in the range when n is bigger than 1, it means that n is an even integer. And as we all know, there's a dichotomy. There's a massive difference between the even values of Riemann zeta and odd values. And Deligne's conjecture tells us about the critical values. And in this case, it predicts a theorem which was known long before by Euler, that the even zeta values are proportional to an even power of 2 pi I, which indeed they are. Beilinson's conjecture about the odd zeta values is much more subtle, and I wouldn't be able to explain it without spending a very large amount of time on background and speaking about motives and extensions and so on. Here's another example that's come up quite a lot in this conference. Let's just take a modular form for simplicity of level 1, but it works in any level. So everything on this page was worked out by Hecker a very long time ago. So F, the modular form, has a Fourier expansion, sum an q to the n, where q equals e to the 2 pi I tor, and tor is in the upper half plane. And we'll assume for now it's an eigenfunction for Hecker operators. So then the L function is the sum of an, it's the same Fourier coefficients here, over n to the s. So it's just the Dirichlet series given by this. But there's a subtlety here, which may look like a typo, but it's not. And that's that you throw away the first Fourier coefficient A0. The L function only involves the Fourier coefficient starting from 1, which seems quite strange, but we'll see why later on. In fact, that definition works for any modular form, even if it's not a Hecker eigenfunction. But when it's a Hecker eigenfunction, then it has a factorization into this product. okay? So this is all Hecker's work. The completed version, lambda, is 2 pi to the minus s gamma s L f of s. And you may be wondering why this might look a little bit different from the gamma factors I had before, but don't forget that there's the duplication formula for the gamma function, which expresses a gamma function, so gamma of 2s as a product of gamma s over 2, gamma of s over 2 plus 1. So one should really think of the gamma factors here actually as a product of 2 gamma factors. And in general, the number of gamma factors is called a rank. So these are really rank 2 objects. And so Hecker also proved that the functional equation is this one here. So the weight is, there's a sign, and the axis of symmetry is 2w minus, there's a fraction 2w minus s. Okay, very classical. Oops. Okay, so now I want to tentatively feel my way towards possible mixed L functions. As I say, there's no definition out there, and there's no at most noises in the literature that such a thing might exist. I'll say a bit more about that, but there isn't. It's not clear whether such a thing should exist at all. But if it did, we would want it to be related to periods. So I'll start with some caveats of what the definition is not going to be. So the first class of mixed periods that aren't sort of classical L values that we already know about, that we'd want to consider are multiple zeta values. So I think everybody's seen these before. They are periods of possibly the simplest possible types of mixed motives we know about, mixed Tate motives over the integers. And so any theory that we come up with had better capture these numbers, otherwise we're in all sorts of trouble. So we want to get multiple zeta values as values of our mixed L functions, at the very least. And a naive answer to this would be just to simply do like the Riemann zeta function and replace the indices with an S, and look at what's called a multiple zeta function. Now, in fact, these do have a meromorphic continuation. I think that was proven by Zhao. But they have poles along infinitely many hyperplanes. And that is bad. So I put, I'm sorry, this bad exclamation mark reminds me of a sort of Donald Trump tweet. And I apologize for that. I've got a few exclamation marks throughout my lecture. So if someone could do a little cartoon Donald that we could put in the corner with good or bad exclamation mark, then it would spice up the talk with some value judgments. But in any case, I would like to think that this is not the sort of thing that we want to consider. And there is no known functional equation for these as of yet. So they are not going to be examples of the mixed L functions I want to consider. This is not the definition, okay? Here's another thing you might do along the same sort of line of reasoning. You might want to just try and define a double L function. Take two Dirichlet series, L1 and L2, with coefficients an and bn, and consider this sort of nested sum, this nested Dirichlet series. So people have done this. There's a literature on this. This is not the definition I want to take in this talk, but it does happen. There are certain particular circumstances where the definition I'm going to give happens to give formulae of this type. And this occurs, for example, if L1 and L2 correspond to Hecker eigenforms and S1 is an integer. So sort of by accident, in this case, I can actually prove that this function has an analytic continuation and some kind of functional relations. But that's just an accident. Okay, so that's not what the definition is. Now, what is the definition? So the idea is to use integrals rather than sums, and follow Docchester and Zagier, who use this technique for computing L functions to very high accuracy. And you can write, we're going to assume all the functional equation and analytic properties of lambda and write it as a Mellin transform. So it's an integral from 0 to infinity of a certain kernel theta, t to the s dt over t. And this function theta, you can write it down. It's just some an, these are the same coefficients that occurred in the Dirichlet series, times some function phi. And this function phi is typically an exponential. It's given by some inverse Mellin transform of the gamma factors. So the great thing about this is that once you've got, if you're looking at L functions with a certain type of gamma factor, you just compute this function phi once and for all, and then you've got a universal recipe for all your L functions of that type, and you can just write down these theta series. So now what happens is that this function theta 0 can now be completed into theta, what I'm going to call theta m, by adding an extra term theta infinity, which is just a polynomial. So you correct it with a polynomial, and then the completed theta satisfies this very beautiful function equation. But when you inverse t, you get t to the w. That's the same w that occurs in the functional equation for lambda, and the epsilon is the same sign in the functional equation, times theta. Okay, so some examples. For the Riemann zeta function, we have a classical Jacobi theta function. So sum of the integers e to the minus pi n squared t squared. And this you can view as 1 plus all the bits that have a non-trivial dependence on t. So the theta infinity t is this is a polynomial, it's just 1, and the rest decays extremely rapidly as t goes to infinity. And that means you can get very fast conversions. And the functional equation here is this one. In the second example, we had a modular form. The theta function is essentially gives you back the modular form. And when it's a cusp form, there's no zero Fourier coefficient, so there's no divergence at infinity. Okay, theta infinity is 0. And this is the function equation, which is the same one we had before. Okay, so what's the definition of a mixed L function? So we're going to take now a bunch of theta functions, theta 1 up to theta r, and we assume they satisfy a functional equation like this, and that they can be decomposed into an infinite part, which is just a polynomial in t, and the rest, which is going to go to 0 exponentially fast at infinity. And then we can define a mixed L function, tentatively, to be the iterated integral of all of these theta functions times a Mellin variable t1 to the s1 minus 1. So it's an iterated Mellin transform. This may diverge, so we regularize at infinity. And there's a very precise prescription for doing that, which is completely explicit. So in the case of a single function, this regularization at infinity means that you just integrate, you throw away the infinite divergent part. You just keep the exponentially decaying piece, and you integrate that from 0 to infinity, and that gives you back Hecker's original definition of the L function. And I've written here that it's strange, and the reason it's strange is because if you go back to this formula, in the case R is 1, it's completely obvious that the functional equation of theta is equivalent to the functional equation of lambda. If you know something about tangential base points, then it's obvious. But in this picture with theta 0 doesn't satisfy any particularly nice functional equation. It's quite horrible. It's quite surprising that actually the L function, the functional equation of lambda is equivalent to the functional equation of theta. So already in the case R equals 1, this tangential base point business explains something. Okay, so in the case R equals 2, we've got a double integral here. I've spelled out the definition. If you work it out, and this can be done completely explicitly, you get these completely explicit integrals, there's 2 of them in fact, and you'll notice that in the upper variable is t2, we've got a theta 0, and that's the one that tends to 0 exponentially fast at infinity. So that's going to enforce the very rapid convergence of these integrals at infinity. So this theta 0 here and here are going to crush this integral and make it really super fast convergent. Great. So here's a theorem that's, I'm sure, obvious to many of you who know about iterated integrals. It's not a very difficult theorem at all. That this multiple mixed L function has a meromorphic continuation to complex plane and R variables with poles along only finitely many hyperplanes in the SI, And you can write down what the poles are and what the residues are and so on. It has a functional equation. So now if you take these R variables S1 up to SR and switch the order and flip them, WR minus SR up to W1 minus S1, then you get this functional equation. And also there's a shuffle product formula. So if you multiply two such mixed L functions, they are a sum of other mixed L functions. So they form an algebra. Okay, so there's a definition for what it's worth. I'm not claiming that it's necessarily the be all and end all or the right one in any sense. But I think it does the job in some situations. So that's what I want to discuss now. And the challenge is whether we can relate these to periods in an interesting way. So the first question is like, what values are we going to evaluate these L functions at? And the best possible thing, the most cautious thing one could do is to take all the SI to be to correspond to critical values of the corresponding L function. So we had these R theta functions, each of them correspond to an L function, and Deligne defined what it meant to be critical. So we want all the integers to be critical, and that's what I mean by totally critical. So we get a bunch of numbers. So what can we say about these? So the first example is going to be the case of modular forms, just of level 1, but it could be any level. So in level 1 for the time being, if we take F1 up to FR Hecker eigenforms of weights W1 up to WR, then the multiple L function satisfies this functional equation. And the totally critical values, in this case, are just the integers that are completely inside this critical box. So it's not a critical strip now, it's a critical box because it's higher dimensions. So you look at all the values within this range. They're strictly inside the box. And in fact, Manning wrote down the definition of these L functions a while ago. In fact, in the case where they're cusp forms, so there's no regularization to be done. And in this case, you can show that the values are indeed periods. They're periods of the relative completion of the fundamental group of a modular curve. So in more sort of layman's terms, they are iterated integrals of modular forms, of sections of certain algebraic bundles on modular curves, and they're absolutely periods in the sense that we would want. So that something certainly works in that situation. Now, a very recent theorem by a PhD student of mine who's just completing at the moment, Alex Saad. It's a very beautiful theorem, and he proved that all multiple zeta values can be expressed as linear combinations of iterated integrals of Eisenstein series. Okay, so this is subtle because there are many iterated integrals of Eisenstein series which are not multiple zeta values at all. You can get non-critical values of cusp forms. So the proof is very beautiful, it's rather tricky. But what it implies is that we can get all multiple zeta values can arise as the totally critical values of these mixed L functions occurring, coming from Eisenstein series. So here's an example. Zeta of 3 is, as I'm sure many of you know very well indeed, Zeta of 3 is an Eichler integral of an Eisenstein series of weight 4. I think this goes back even to Ramanujan. So that's a prototype, and Alex has shown that this is true for all multiple zeta values. So the first test has been passed. We have managed to construct all periods of mixed state motives over Z, also known as multiple zeta values. We have managed to capture them as totally critical values of mixed L functions. So that's a bit of hope. Okay, so modular forms were maybe tricky, so let's step back a bit and go back to the trivial motive and see what this definition gives. And already it's surprisingly interesting. So I remind you that the trivial motive, which is just a point, it's got no geometry at all, a point already generated the Riemann zeta function. And the Mellin transform of the inverse Mellin transform of the Riemann zeta function was this Jacobi theta function. Okay. So let's take iterated Mellin transforms of this Jacobi theta function. And you could call this function the multiple Riemann psi function, because in the case r equals 1, it gives the function that Riemann defined. And it satisfies this function equation here. Psi of S1 up to SR is psi of 1 minus S1, 1 minus S1 minus S1. And now if you was thinking along the lines of the previous slide, where the totally critical values were the ones inside, strictly inside the box of the function equation, you'd be panicking because there is no integer within that's within the box. There's no integer strictly between 0 and 1. So it looks like there's nowhere interesting where we could evaluate this function. And I'm going to come back to that in a little bit later. But don't forget that critical in the case of the Riemann zeta function does not mean inside the critical strip. It means being positive even or negative odd. So totally critical means that the positive, we should look at the arguments where all the SI are positive even. So the question is, like, what can we say about the values of this function for even SI? And we cross our fingers and hope that they're periods. And let me just focus on the case r equals 2, which is rather nice because here's the function equation and here's the shuffle product formula. It's a rather nice little set of properties. You can also show that the residues of these functions along hyperplanes give back the classical Riemann psi function. So in fact, in general, if you look at these totally even values, they can always be written in terms of what I call multiple quadratic sums. So I only wrote down the case r equals 2 here, but then they're nested sums, a bit like a multiple zeta value of, now instead of putting an integer to a power, you have this quadratic term, k1 squared plus k2 squared. And in general, you'd have k1 squared dot 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 up to kr squared. These things turn up a lot in study of lattice sums. They're connected with some questions various questions in physics. In this case, you can show that this double psi function in 2 variables is something very, very simple. It's just a Mellin transform of a real analytic Eisenstein series. And real analytic Eisenstein series we've seen a lot because it comes up all over the shop in string perturbation theory, so it's been in many of the talks already. And it's a really fun exercise to check that the two function equations I wrote down here follow from 2 properties of the real analytic Eisenstein series: its function equation and its modularity. And it's a very, if you knew this definition, this formula in advance, you'd very, very easily deduce these 2 formulas. It's quite fun. In any case, if we put SI to be integers, we deduce that the totally even values are Eichler integrals of not real analytic Eisenstein series, but holomorphic Eisenstein series from I to infinity. Okay, so if I were to integrate from 0 to infinity of a holomorphic Eisenstein series, I would get a power of pi, or I'd get an odd Riemann zeta value. But here we're going to integrate from I to infinity. And what that means is that these numbers are related to iterated integrals on this complex multiplication elliptic curve, whose period lattice is the Gaussian integers. So it's related to, you get L functions of Grossen characters of this elliptic curve showing up as periods occurring in this multiple Riemann psi function. So we're in business here as well, and maybe it's not surprising that if you look at this formula that you should get something to do with Gaussian integers. Okay, so that one works as well. Here's something I'd like to put out there that generalizes the 2 previous examples. So it's what I'd like to call multiple Jacobi values. So we saw that the Riemann zeta function, just going back again, the theta function was just one of Jacobi's theta functions. Well, why not consider all 4 of them? So here they are. They're the theta null values They go back a very long time. So now we have three theta functions. There's a little caveat here, which is that they're not self-dual. So if you look at theta of 1/t, that may be related to one of the different theta functions. So I didn't talk about that. I assumed self-duality at the beginning, but this is absolutely no problem. And it's very, very easy to deal with. Another issue is that these actually have half integral weight. So the sort of divergence at infinity is not a polynomial in t, but you may get something in square root of t. But so what? That's not a problem. We can just replace the square root of t with t. And these issues really are very trivial indeed. So in any case, it's very natural to consider the Jacobi theta functions. And we can look at the algebra they generate, and we can define a multiple Jacobi value to be any totally critical value of the multiple L function of a sequence of R such theta functions. Now, these numbers are going to satisfy an incredible set of identities. First of all, the theta functions alone satisfy extraordinary identities that have been explored throughout the ages. The L functions even more so. In particular, we already know, because you can actually write modular forms, all modular forms as polynomials in theta functions. This is going to contain all the previous examples we looked at, namely the case of modular forms and the case of the Riemann multiple psi function. And by Sard's theorem, we know that multiple zeta values occurred as in the first example, as where the theta I were Eisenstein series. So this is a vast generalization of the last two examples. But the multiple zeta values occur in a completely different way as well, which I think is quite striking. If you take theta 3 to the 4, there's this particular combination of Jacobi thetas, you get a pair of incredibly simple weight 2 theta functions that I call theta plus and theta minus. And they satisfy this function equation and this function equation with a minus for minus and a plus for plus. And their L functions now have the nice property that it relates S and 2 minus S. And the reason that's nice is because now you have a very natural point at which you can evaluate them, namely S equals 1, which is slap in the middle of the function equation. And in fact, if you would to try to cook up an L function which satisfies this function equation and has no pole at S equals 1, this is basically the simplest possible thing you can do. So you have a very natural pair of theta functions, plus and minus. And if you consider the the mixed L functions associated to them, they have a unique central point, 1, 1, 1, 1, 1, which is completely symmetric with respect to the function equation. And if you evaluate these numbers at that point, you find, miraculously, that you get exactly multiple zeta values and log of 2. These multiple Jacobi values are going to contain multiple zeta values in two completely different ways. The first, var Sard's theorem, var modular forms in some subtle way, and here in quite a direct way, using the fact that P1 minus 3 points can be uniformized using these theta functions. So these multiple Jacobi functions, multiple Jacobi values contain, they see the geometry of the moduli space M04, P1 minus 3 points. That's this theorem. But they also capture everything to do with M11, so genus 0 and genus 1. And that's why I think that if someone does choose to explore these numbers, I promise you, you will not be disappointed. There'll be all sorts of theorems that will fall into your lap. And I think it will be very connected to some of the themes of this conference because it speaks to genus 0 and genus 1. Good. So now I'm going to switch topic momentarily. So I discussed classical L functions and defined some multiple version of them. Now I'm going to do something different. So to motivate this, let's just flick back. So Hecker, what did Hecker do? Hecker, who was just thinking about modular forms, of course. Sorry. Here we are. So Hecker took a modular form and he wrote down a Dirichlet series, this one, and realized that the modularity of F, namely the symmetry with respect to tau goes to -1/tau, gives this functional equation on the L function. And his definition, the recipe to get the function lambda from F was, here it was, is basically a Mellin transform. So we can do the same thing, but we can try this with not a holomorphic modular form, but we could try this with a real analytic modular form. Okay, so this is a priori something completely different. And the relevance to this conference is that you could take a modular graph function that occur in genus 1 string perturbation theory, about which we've heard many talks. Or you could take a modular graph form, and that's going to give you an L function. Okay, so let's do it. We can take, in fact, any real analytic modular form and try this idea. So for me, a real analytic modular form is a function from the upper half plane to complex numbers that is real analytic, and it has modular but with two weights, W and W prime. So if you apply a modular transformation, Möbius transformation, then you get back the same function, but multiplied by a holomorphic automorphy factor, C tau plus D to the W. So this is very familiar from the classical theory of modular forms. But what's new is this anti-holomorphic transformation factor, C tau bar plus D to the W prime. I also want it to have an expansion. So people sometimes call this a Fourier expansion. I don't know why. It's strictly speaking not a Fourier expansion, but I may lapse and call these coefficients Fourier coefficients. I think we tend to think of them as kind of generalized Fourier coefficients. But the expansion is that it's a polynomial, so it has a finite number of terms of some power of the imaginary part of Z times some power series. So a two-dimensional power series in Q and Q bar. So a classical holomorphic modular form would have no Q bar dependence, and we wouldn't allow any powers of any imaginary parts of Z here. Okay, so the summation range for K is finite, but the M and the N's go off to infinity. And I need a very, very weak condition on the coefficients that they don't grow too fast. So these conditions are amply satisfied for modular graph forms. That's certainly known. So modular graph forms, modular graph functions are certainly examples of such functions. So what we do is take these coefficients and we can, so for each K, we can package them into a Dirichlet series. And the funny thing is here about it is that you don't, these L series, there's one for each K. So I remind you K is, oops, my mouse. K is each term here, each power of MZ. You get one Dirichlet series for each K, and these coefficients A don't all play a role. It's only the sum of them. It's only the sum of A, M, N such that A, M plus N is a fixed number that occur. So you lose a whole lot of information when you form this Dirichlet series. And then we can define the completed L function to be a finite sum of some power of pi and some gamma factor times this very explicit Dirichlet series. Okay, so the key point is, does not depend in this formula. Nowhere do you use any of the what are called the zeroth Fourier modes. They simply don't arise in the formula. The L function does not depend on them at all. And in fact, it doesn't really depend very heavily on these Fourier coefficients. It only depends on certain sums of them. This is not a classical L function. It's because it's a sum of, it's got different gamma factors coming in. It certainly doesn't have an Euler product. So a theorem, it's really easy to prove this theorem. So I called it a proposition. I was too embarrassed to call it a theorem. It's stated, it's very easy to prove. It's stated in a paper of mine called a class of non-holomorphic modular forms. It's not in the archive version because it was a bit of an afterthought. So it's in the online version. If you want to look at this, don't look at the archive version of that paper because it's not in there. So the statement is that this L function has a meromorphic continuation to the complex plane, and it satisfies the functional equation. All right, no big surprise there. It also has simple poles with, and the principal part, in fact, gives back exactly all the zeroth Fourier modes. So that's kind of fun because it means that in recalling the definition of the L function, it didn't use the zeroth Fourier modes at all. So this L function gives us a recipe that if we know all the other Fourier coefficients for m n bigger than 1, then we can reconstruct the zeroth Fourier modes by forming the L function and taking its residue. So I think that might be of some use. So here's an example. Let's look at a real analytic Eisenstein series. So E, I like to take it with different powers, W and W prime here. Classically, you take W equal to W prime, but it can be a bit more general. This has modular weights W, W prime, and it turns out that its L function is a product of two Riemann psi functions. And so that explains a lot of stuff because it explains why if you look at the Fourier expansion of a real analytic Eisenstein series, you know that all the Fourier coefficients are rational, but the zero modes are zeta values. And that of course follows from the previous proposition because the zero Fourier modes are just the residues of this psi function, and it has exactly two poles. There's one pole coming from this psi function, there's a pole coming from the other one, and you get an odd zeta value and you get an even zeta value respectively. So it explains precisely where these zero Fourier modes are coming from. So in generally, to any modular graph function then, we can associate a completed L function. And I think it's going to be interesting. I've not tried to compute any. I would be delighted if someone wants to do that. One thing I can say in favor of this is that, in fact, if you apply these Cauchy-Riemann differential operators, like these raising and lowering operators on these modular graph forms, you get a very nice relation between their L functions. So these L functions reflect the differential structure in a nice way. Okay, so let's wrap it all up. I've defined different types of L functions now in this talk, and it turns out that they're all connected to each other. So the next theorem, so let's take my favorite family of real analytic functions, real analytic modular forms, actually not so easy to construct. But there's a very canonical supply of real analytic modular forms, and they come from elliptic curves, which is one of the themes of the conference. So how do you do that? Well, you take the universal elliptic curve, E tau, you puncture it, and you consider all iterated integrals on it, which are single valued. Okay, so that means you take an iterated integral on your elliptic curve, and we have to be a little bit careful about tangential base points and so on, because we've punctured the curve, but let's not worry about that. This is a very canonical thing to do. So we take, in mathematicians' parlance, we take the pro-unipotent completion of the universal elliptic curve, punctured, and look at its single value periods. So those are numbers. because we've integrated from, around a loop on the curve, if you like. Now, if we now vary the parameter of the elliptic curve, we're going to get functions on the upper half plane. And those are precisely a very special class of real analytic modular forms that I call MIE, which are what's known as what I call equivariant iterated Eisenstein integrals, because you can show that they are iterated Eisenstein integrals, which are equivariant, which means modular. So this is the universal, a universal family of such real analytic modular forms coming from elliptic curves. And if you compute the L function of them in this non-standard L function, then you can show that actually what you get back is a mixed L function, as I defined in the first half of the talk, associated to a bunch of holomorphic Eisenstein series, in which you hold all the values S, all S1 up to Sk minus 1, constant, and you only allow the last parameter to vary. So that's yet more evidence that these mixed L functions, at least in this modular case, are doing something really interesting. So if you like, from this theorem, we get a prediction. If you have any modular graph function and compute its L function in the way I explained, then that is going to be a linear combination of these mixed L functions of Eisenstein series. So conclusion, what we did is we started off with the very classical theory of L functions, which goes back many centuries. And by passing through their Mellin transforms, we wrote them as integrals, inverse Mellin transforms. We wrote them as integrals and defined mixed L functions as the iterated Mellin transforms of a bunch of L functions. Now, I should say, I have no idea whether this is the right thing to do. If you take motives of rank 4 or higher rank, I have no idea whether for R bigger than 1, this is the right object or not. That's why I'm very cautious. But I think this is a first step in the right direction, because as we've seen, these functions satisfy many nice properties. And in the case where the underlying L functions are rank 1 or rank 2, they're totally critical values connected to many very interesting periods. They related to string amplitudes, as I mentioned, to elliptic iterated integrals on the previous slide. They relate to modular forms, they relate to lattice sums, and they relate to many topics which have come up in various talks in this conference. And so the bell has just rung, and this is a perfect place to stop. Thank you very much for your attention.
Yes, thank you very much, Francis, for this talk. Let's unmute for a moment in order to exert our applause. I'm sure there is a lot of questions for this talk, but before we get to the questions, I would like to take the opportunity to thank all the speakers and all the participants for their talks and contributions to this conference, for the discussions, and for all other help and input. I experienced this conference as a very vibrant and colorful conference, and I hope we somehow managed to understand the respective languages a little better. At this point, we as the organizers would also like to thank Olli C. Sorli and Felix Achtmann in Mainz for their administrative and technical support. In particular, there will be videos of the talks, and they will be published on the MITP, that is the Mainz Institute of Theoretical Physics, YouTube channel in the very near future. So far, nothing is online, but it will be there very soon. Okay, so thanks to everybody who made this a very nice week. Now, Yeah, this is an online conference. Now we should get back to the questions for Francis. And David Broadhurst has raised his hand. David, please.
So thank you, Francis. My question concerns the first part of your talk. And the big message I picked up there is that we should be critical about our use of the word critical. And that resonates back, if you remember, to 2010, when I was asking you about the magnetic moment of the electron at 4 loops, and later we went to 6 loops, and morally what we should have been doing on the edge of the strip, but we ended up at pi squared times something inside the strip. And then later, Anton Mellet and David Roberts and I showed that you can actually get outside the script and engage with things which Fernando had done. So my question is, can you get outside the critical box?
That's a very good question. I don't know. I don't know anything about values of L functions outside the critical box. Well, and that aren't totally critical in the case where R is bigger than 2. I do know about something outside the box. The Riemann-Xi function, remember, I know something about even, comma, even, and they can be outside the critical box of the functional equation. And that was the motivation to study that. But let me provide you with sort of enhance your question and say, well, you could say to me very fairly, what happened to the non-critical L values in the case R equals 1? Because there's Beilinsen's conjecture. I can't just throw it away. And it turns out that those non-critical values in all these cases show up as totally critical values of a double L function. So everything you had in the classic for classical L function, R equals 1, you have the critical values, and then the non-critical values. All the non-critical stuff shows up as double L functions. And so in fact, you only need to look at the totally critical values. And that's why, so an answer to your question is, I don't know anything about any non-critical values, but I'm not too worried because I haven't thrown anything away.
Okay. There's another question from Lance. Lance, please.
Hey, Francis.
Hi,
thanks for that fascinating introduction to this developing general theory. I was wondering if you can imagine something a little less general. Suppose I want a machine that produces multiple zeta values, but not all of them, but some subset that's closed under a coaction. Is it possible that that could be related to some subring in these theta functions that are associated to it? And you know, similar things in the larger non-multiple zeta value context, like electron G-2 or phi to the 4th periods?
That's a very good question. I don't know the answer to that. I had nothing particularly intelligent to say about that. So off the top of my head, I would say one thing, that you can, that the normal way we write zeta values is with this indexation n1 up to nr, and the index r is the depth. And the depth is motivic, which means that it's preserved under the coaction. I had a theorem somewhere, if I can, I had a theorem somewhere here, that there was a different way of writing them as iterated integrals of these theta plus and theta minus. Now, if you translate this back, this means you take not dz over z and dz over 1 minus z, but they're symmetrized and anti-symmetrized versions with respect to z goes to 1 minus z. And you get a new filtration. You can count the number of pluses and number of minuses. And I think that's, I think so. My Adam Kilty, I think, checked that is motivic as well. So you get some new filtration on multiple zetas, which will be stable under the coaction. So yes, I think that your question is a great question. I'm sure stuff like that is out there, but I don't have anything in mind apart from this very special situation.
Great, thanks a lot.
Yeah, maybe Niels.
Hi, Francis. Good to see you again. Thanks for a great talk. So I think my question is rather ill-defined because I'm asking about something which you haven't really defined in your talk, as you admitted, the mixed L functions. So, but to a mixed motive, you've associated a mixed L function. Can you go the other way? Can you reconstruct the motive from the mixed L function?
Good question. Sort of. So if you, I mean, intrinsic in the definition of the mixed L function is the theta functions, right? So they each correspond to pure motives. So if you've got the constituent pure motives, right, which are the building blocks of your mixed motive, and then you need to glue them together. You need all the extension data. Well, the extension data by Beilinson is encoded by the regulator, which is the value of the L functions. So, and since you know you've been given the values you're evaluating it at, you know something about the extensions as well. So I don't really know the answer to your question, but it's going in that direction. It's heading in that direction.
Okay, thanks very much.
Yeah, Claude, you had a question.
Yeah, hi Francis.
Hi Claude.
So I've understood correctly, so you started off by saying, well, if I take the classical theory of my L functions, which give me periods, at least if I evaluate them with special points, and I said, well, what about the kind of converse question? So can my periods, could they come from some hypothetical extension of my theory of L functions? And you gave a candidate, and you were very careful to say, well, this may not be the end of the story. But let's assume that this was really the end of the story then. And all these things that you defined were iterated integrals.
Yes.
Would it mean, would that have some implication? For example, what about things like, I know, let's say a complete elliptic integral, which are some periods, but which I would not naturally see as an iterated integral of some sort, or what would that imply? So usually I think of these things as certain things which are like iterated integrals and certain things which are not, which may not be the right way to think about it. Well, what you said now is, well, if this was the right picture, they would all be iterated integrals of some sort.
Yeah, so I'll say two things in response to that. First of all, if this were the right picture, things go a bit weird in higher rank, and that's what makes me nervous. In the case of rank 1, the zeta theta function, so the Riemann zeta function, we got a Jacobi theta function. So that's not a very algebraic thing. It's something. It's not a very nice algebraic object. In the case of cusp forms, those Hecker eigen modular forms can be viewed as something algebraic. So we get iterated integrals of something that looks algebraic. They're kind of periods. You know, if you start with a higher rank motive, a rank 4 motive, these theta functions are not algebraic at all. They look scary. They've got sort of Bessel functions and stuff. They've got Fourier expansions involving weird Bessel functions. So an iterated integral of those would not, in any obvious way, be an iterated integral of something algebraic. So perhaps these examples are slightly misleading in that respect. But the other thing I would say is that in some sense, there is a sort of very philosophical sense, but well, there's a technical sense in which all periods are iterated integrals of something. And the reason for that is because this is very technical, but there's a way to construct mixed motives as the bar construction on a cycle complex of something that computes K-theory. So what that means is that mixed motives should be something like iterated integrals on something which computes pure motives. And if Beilinson is right, there's something that computes pure motives are L functions. So it has to be the case, I'm sure it's the case, that all periods of mixed motives are somehow iterated integrals of something. The question is there something that I've written down the right one? And in the case of, as I've said, in higher rank, rank 4 and above, I'm nervous, which is why I'm cautious. But you know, even a single example would be fantastic to either refute or confirm. So that, yeah, that's what the answer is sort of yes and no, if that makes much sense.
Okay, no, I think that that answers the question at least. I mean, I don't know the details of what you said, but when you say, okay, there is something like a bar construction that should also do these things, I can live with that, yes.
Yes. Are there more questions from the audience? No? If that's not the case, then let's thank Francis again and unmute again. Yes, and the Zoom room will be open for a little longer for those who want to stay, but that is the official end of the Elliptics and Beyond conference 2020. Thanks again all for coming and contributing, and thanks for all the talks.